Hello students, I'm Akash again and I welcome you all on PhysicsWallah with third chapter of electrodynamics, which is capacitors. Capacitors are actually the third and very important elements of electrical circuits, the first being batteries, the second being resistance and third capacitors. What battery does? It provides electrical energy but at a constant and slow rate. Okay. What resistance do? They dissipate this energy and give us heat or light. Okay, but what capacitors do? Capacitors store electrical energy in electrical form, which battery don't, because battery stores energy in chemical form, and through some chemical reactions it provides electrical energy. It converts its chemical energy into electrical energy and provides at a constant and slow rate. But what if we require a lot of electrical energy instantly? The answer is in capacitors. Okay, so in capacitors we are going to cover definitions of capacitors and their capacitances. Capacitance is a property, or you can say physical quantity related to capacitors. Capacitors, then we will study how capacitors behave in circuits, how they work in circuits, and how the energy is stored, what energy they store actually. Then we will learn what is the role of dielectrics in capacitors, and finally the RC circuits, means circuits involving resistance and capacitors both. Okay, so let's begin. Okay, let me tell you a simple application of capacitors that will prove their importance. Okay, suppose we have a camera, a old one. Okay, suppose we have a old one, a 10 years old camera, and you suppose it is working, right? So if you take the bulb of the flash bulb of the camera and take the batteries out, okay, and connect the bulb across the batteries, you won't believe it will glow with a very low light. Okay, because battery provides energy at a very slow rate. Okay, but when you operate the same bulb, the same flash bulb in camera during photo shoot, and when you press the flash button, the same bulb with the same batteries glows with a million times more brightness. So why it is so? We have same battery of camera, we have same bulb, but when we connect bulb with batteries, it glows with very low light. But during flash, during photo shoot, when we operate flash, the same bulb glows at a very large or very luminous light. How? The answer is capacitors. What capacitors does? Capacitors slowly takes energy from bulb and the cell. Capacitors slowly take energy from cell. It stores that energy into itself. Okay. It takes seconds to store energy inside the capacitor. And when flash is operated, the cell doesn't provide that much energy, and the energy which was stored in the capacitor is instantly, or you can say only in few milliseconds, the whole energy that the cell provided in say 4 or 5 seconds, the whole energy is dissipated in the same flash bulb within milliseconds or microseconds. Okay, so that was the reason flash glows at a very high brightness. Okay, so I think we got the idea. Let me take another example. Suppose we have a water purifier at our home, and if you on that water purifier, and suppose water is coming out. If you have to drink water, a glass of water, you just put your glass of water under the tap and you wait. Okay, and when the glass is full, you drink it and it's okay. But suppose you have a party at home, there are 20 guests which are coming, and 20 guests have to drink this water almost at same time. But if they all stand in queue and wait for their turn, it would take maybe half an hour or 1 hour to for everyone to drink water. So what you do actually, you start preparing for this event from the morning. What I would do actually, I would take a bucket or a water storage, put it under the water purifier, and in 1 or 2 hours, the pure water will be filled in that storage, and when the water is needed, the pure water will be provided instantly to all the guests. So that is the purpose of capacitor in electrical circuit. Okay. Suppose we need a lot of energy, but battery will give this energy in a very large time, because battery gives energy at a very slow rate. So what capacitors does, capacitors take the energy from battery, store this energy in themselves, and provide this energy instantly or within almost no time to the circuit whenever it is required. And that's what capacitors were doing in case of a camera. Okay, they were taking energy from a cell in maybe 4 or 5 seconds and deliver that energy, the same energy, in few milliseconds. So power is increased multiple times. Okay, so let me now tell you what are the exact definition of capacitors and how they behave in circuits. So capacitors are basically two conductor devices. In capacitors we have two conductors with some charge, okay, with some charge. Usually on capacitor conductors we give equal and opposite charge, like one is given plus Q charge and other conductor is given minus Q charge, and those conductors are placed at some gap, at some distance, or you can say with some insulation between them. Okay, so capacitors are basically two conductor devices with some gap in between and have charges plus Q and minus Q on its two conductors. Okay, they are used to store electrical energy and used when the entire energy is needed in a very short span of time. Okay, because battery cannot do this. Battery will give you energy, but they will do at their own rate. But capacitors can deliver all the energy within no time, or within few milliseconds or microseconds. Okay, so remember this, capacitors are basically two conductor devices having plus Q and minus Q charge on their two conductors, and there is some gap or insulation between capacitors. Okay, suppose these are the two conductors of a capacitor. One has plus Q charge, the other has minus Q charge, and they are placed at some distance. So if one is charged positively, the other is charged negatively, there will be some electric field in between. There will be some electric field lines, right? And as you know, along electric field lines will definitely start from positive charge, positive conductor, and they will terminate on negative conductor, right? And along electric field line, as you all know, potential decreases. So there will be some potential difference between this capacitor conductors. So plus and minus denotes here at positive conductor we have bigger potential, and at negative conductor we have lower potential. Suppose this potential difference is V. Potential difference is V. So what we experimentally find is the potential difference on the or between the two conductors of a capacitor is directly proportional to the charge on capacitor. Actually, if you see closely, the total charge on the capacitor is 0, because one conductor has plus Q charge and the other conductor has minus Q charge. But whenever we say what is the charge on capacitor, we say the magnitude of charge on any one plate, or you can say the charge of positive conductor plate is called charge on capacitor. So I can say the potential difference across the two conductors is directly proportional to Q. This is a, you can say, an experiment result, right? And when I use a constant of proportionality 1 upon C times Q, okay, so Q becomes P times V. Q is the charge on capacitor, V is potential difference between the two plates or two conductors of capacitor. The C, the constant of proportionality C, is called capacitance of this capacitor. C is capacitance of capacitor. As you can see, the unit for capacitance is coulomb per volt. Coulomb per volt. Okay. But we measure this capacitance by a unit called farad in SI system. So actually, coulomb per volt, let me write it here. The unit of C is coulomb per volt, and this is also called farad, and simply F. Okay. So SI unit of capacitance is farad. Okay. Let's move a little. Suppose I have a single conductor, a single spherical conductor of radius r. This can also be called a capacitor. Okay. And when we say this a capacitor, we assume the second conductor is a very large spherical shell of almost infinite radius. Okay. So if this is called a capacitor, suppose we give it a charge q, we assume the minus q is at infinity. Okay. And obviously, you know the potential of this conductor is given by K Q by R, or simply Q divided by 4 pi epsilon naught R. If you compare this equation by V equals to Q by C, the capacitance of this single spherical conductor would be actually 4 pi epsilon naught R. Okay, so this is the capacitance of a spherical conductor. Okay, let me just give you a little idea how much is 1 farad. Okay, so suppose I take a sphere whose capacity is 1 farad. Let me tell you one more thing. When we talk of a single conductor capacitor, its capacitance is generally known as capacity. Okay, so always remember, whenever we talk about a single conductor capacitor, we don't talk about its capacitance, but the same thing here is called capacity. Okay, so capacity and capacitance are usually same, but if we have two conductor capacitor, we call it capacitance, we call its capacity as capacitance, and if we have a single conductor capacitor, we call its capacitance as capacity. Okay, so the capacity of a single conductor capacitor, a spherical conductor capacitor, is this. If suppose I have a sphere large enough such that its capacity is 1 farad, okay, then its radius would be C divided by 4 pi epsilon naught. If C is 1 farad, and you know 1 upon 4 pi epsilon naught is 9 times 10 to the power 9, so we will be having this radius. Means a sphere of, I think, 9,000 megameters or 9,000 million meters will be having a capacity of 1 farad. So actually 1 farad is very big. The unit 1 farad is too big that the usual capacitors that we find in market are usually in microfarads or nanofarads or sometimes picofarads. Okay, so capacitance 1 farad is really big. Okay, so that's one example, and you should remember this also, that capacity of a single spherical conductor is given by 4 pi epsilon naught times its radius. Okay, so let's move a little. The most famous shape of capacitor is a parallel plate capacitor. So it's again very important for our course also. So here we have two plates. Okay, we are actually looking on the side view of the plates. So plates are like this actually. The plates are like this. The area actually we are not able to see because we are looking at the side view. But suppose this is the area of the plates and the two plates have actually the same area. And the gap between them is say D. Actually, when we talk about parallel plate capacitor, we consider the area is very large as compared to the gap between them. Okay. So when in such cases, I give one conductor a charge Q and other conductor a charge minus Q. In Gauss's law, you must have studied that the Q charge or the plus Q charge comes to the inner surface and this minus Q charge also comes to the inner surface. Okay, and there exists an electric field from positive charge to negative charge, and if again, let me repeat it, if again the area is too large as compared to the gap, the electric field in the middle region is almost uniform, and this electric field is given by charge density divided by epsilon naught. What is the charge density? So Q is the charge, A is the area, so this is the charge density, and divided by epsilon naught, this is the electric field, this is the value of electric field in the region between the capacitor. Okay. If we want to find the potential difference, as electric field is uniform, the potential difference by integral E dot dr can be written as E is constant, take E outside, and integral dr would be equal to D. So V equals to ED. Let me write V equals to E, which is Q divided by epsilon naught A times D. Right. Now, if you compare this equation with V equals to Q by C, by comparison, you would see the capacitance of this parallel plate capacitor will be equal to epsilon naught A by D. So, capacitance of a bigger area capacitor is more, and a smaller gap capacitor is again more, because C is inversely proportional to D and directly proportional to area. So bigger the area, bigger capacitance, is smaller the thickness, or I must say the gap, is smaller the gap, the bigger is the capacitance. So you remember this formula, that's very important. The capacitance of a parallel plate capacitor as epsilon naught A by D, where epsilon naught is your famous permittivity of free space. Okay. Spherical capacitors, though they are less common, okay, but still there is a concept of spherical capacitors. So if we have two concentric metallic spherical shells, they are concentric, and say the area, the radius of the smaller shell is A, the radius of bigger shell is B. So these two shells behave as two conductors of capacitor. So if I give one as plus Q charge, the other as minus Q charge, there will exist some electric field in the region between the shells. And I think you remember, if we want to find potential difference between the shells or between the conductors, the potential difference only depends upon the inner charge. That I told you in the first lecture also. The potential difference depends upon the inner charge only, because of outer charge. Because of outer charge, potential is same everywhere inside. So difference of potential will be because of inner charge. So because of inner charge, the potential of inner shell would be Q divided by 4 pi epsilon naught A minus the potential of outer shell, again because of inner charge, would be Q divided by 4 pi epsilon naught B. Let's take Q divided by 4 pi epsilon naught common, and you will have B minus A upon AB. And if you compare this with Q by C, you will notice C equals 4 pi epsilon naught AB divided by B minus A is the capacitance of a spherical conductor. Okay, that though it is not very important you remember the proof, I think you should just only remember or memorize the formula. Again, in application it is very common to use cylindrical capacitors. In cylindrical capacitors, we have two metallic cylinders. Say one has radius A and outer cylinder has radius B, and if it has a length L. Okay. So capacitance of this capacitor is given by 4 pi epsilon naught L divided by ln B upon A. Okay, 4 pi epsilon naught L divided by log B upon A. So you can say capacitance per unit length. Capacitance per unit length. Per unit length becomes C or dC by dl. It becomes 4 pi epsilon naught divided by ln B upon A. So this is the capacitance, but not capacitance, capacitance per unit length of a cylindrical capacitor. Here we have assumed the length to be very long as compared to radii of the two cylinders. Okay, so now we'll learn the force between the plates of parallel plate capacitor. Actually, as you know, if one plate is positively charged and other negatively, they will definitely attract each other. So if we want to know the force between them, let's suppose one has charge plus Q and other has charge minus Q. Okay, and if the area of capacitor plates is too large as compared to the gap between them, obviously the field, the electric field between them is almost uniform, and this electric field is equal to Q by epsilon naught area, and this I told you maybe few minutes back. Okay, but this field is actually the net field inside the capacitor, and this field has contributions of field because of plus Q and contribution of field because of minus Q both. So this is the field, this is the net field, and it can be written as field because of plus Q plus field because of minus Q. So the net field because of this charge plus this charge is Q by epsilon naught A, right? But if we want to know what is the force on minus Q charge or force on plus Q charge, because that is the force between two plates of capacitor. Actually, on minus Q charge, only the field of plus Q charge will apply force on minus Q charge. Or you can say on plus Q charge, only the field of minus Q charge will apply force. Okay, actually in the net field, the field of both charges is added. So if we want to calculate the force on any one charge, we will have to know the field because of only one charge. And because of the symmetry of the problem, both the charges will produce equal electric field in the middle region. So I can say the field because of only plus Q charge will be equal to half of the E net, which is Q by epsilon naught A by 2. This is the field because of only plus Q charge, and this is the field that will apply the force on minus Q charge. So you can say the force on minus Q charge is equal to, I'm actually looking for magnitude only. So force on minus q charge will be equal to the magnitude of charge multiplied by field because of other charge. Because I think you know the charge's own electric field does not apply the force on that charge. So field of minus q charge will not push or pull this minus q charge. The field of plus q charge will attract minus q, and the field of minus q charge will attract plus q. So this is the minus q charge's magnitude and multiplied by field because of plus q charge, which is q divided by 2 epsilon naught area. So the force is equal to q square divided by 2 epsilon naught times area. So this is the force. Remember this. Okay, and you can also remember that the force is equal to q times E by 2, not q times E, q times E net by 2, where q is the charge on the magnitude of charge on any one plate, and this E is actually the net electric field, and by multiplying it by 1 by 2, it gives you the field of any one charge, and multiplying by q gives you the field multiplied by charge, that is force. Okay, so this is the formula for force between the two plates of parallel plate capacitor. So let us solve few problems that were asked based on the theory I just explained. Okay, the first question is, a parallel plate capacitor has capacitance C. The distance of separation between the plates is D. Potential difference is V, and they are asking us what is the force of attraction between the plates of parallel plate capacitor. Okay, so let us solve this. If we have two plates like this, the gap is D, let's say area is A, and the capacitance is C, and this potential difference is actually V. Okay, as you know, the potential difference is V, so the electric field in between the plates would be V upon D. This is the electric field. Okay, but this is the electric field because of both the charges. The field because of any one charge, let's say field because of plus q charge, will be half of this, that is V upon 2D. Okay, and as the capacitance is C, the voltage is V. As you know, the charge on capacitor is equal to CV by the definition. So actually the plate, positive charge plate will have a charge plus CV, and the negative charge plate will have a charge minus CV. So if you multiply this field with charge, you get force, right? So force becomes the magnitude of charge, that is CV, multiplied by V square upon 2D. Sorry, V divided by 2D, which is electric field. Okay, so answer becomes CV square by 2D. So correct answer is B, CV square upon 2D. Next question. Okay, this is a very general and very common question. Okay, here they say an electron with kinetic energy K1 enters between parallel plate capacitor at an angle alpha with plates. So if you take this as plates of parallel plate capacitor, and an electron enters here like this at an angle alpha, and let's say the speed is V1. Okay, if electric field is upward, suppose electric field is upward, the electron feels a force downward, and because of this force, the path of electron will not be a straight line, it would be like this. It will be like parabola. Okay, and when it leaves capacitor, let's say its velocity is V2, and angle that it makes with initial direction of motion is say beta. Okay, obviously the force is in this direction, perpendicular to plates. So if force is perpendicular to plate, the velocity component parallel to plate will not change. Okay, so velocity component parallel to plates will not change. So let's make velocity component parallel to plate equal. We can write V1 cos alpha 1 equals V2 cos beta. It's not alpha 1, it's just alpha. So V1 cos alpha equals V2 cos beta, right? So I can write V1 by V2 as cos beta by cos alpha. And obviously the ratio of kinetic energy will be equal to ratio of squares of speed, because kinetic energy is half mass times speed square. Okay, so ratio of kinetic energy would be equal to, you can say the ratio of kinetic energy would be equal to ratio square of ratio of speed. So if you square this, you get the correct answer as B, right? Next question. Here they say a parallel plate capacitor has 1 microfarad capacitance. One of plate is given a 2 microcoulomb charge and other plate 4 microcoulomb charge. Okay, that's a very good question. We are giving unequal magnitude of charge on the two plates. One is given 2 microcoulomb positive, other is given positive 4 microcoulomb. So in Gauss's law you must have studied, if you give a pair of parallel plate conductors these charges, okay, the half of total charge resides on outer surface. So the total charge is 2 plus 4, that is 6 microcoulomb. So on outer surface we will have 6 by 2, that is 3 microcoulomb. 3 microcoulomb positive. And by conservation of charge, you now know, if here we have 3 microcoulomb charge, but total we have only 2 microcoulomb charge. So on this surface, on this right surface, we should have minus 1 microcoulomb. And since here we have 3 microcoulomb charge, but in total we have 4 microcoulomb charge, on this surface we must have plus 1 microcoulomb. Okay, so actually the equal and opposite charges are on two inner surface of the plates. So actually these inner surface make a capacitor. The inner surface, not the entire two conductors make a capacitor. Only the inner faces make a capacitor. And if inner plates make a capacitor and they are asking the capacitance is given as 1 microfarad, obviously the potential difference is given by Q by C. I think you remember V is Q by C. The Q here is 1 microcoulomb. The capacitance is 1 microfarad. So obviously the voltage, the potential difference becomes 1 volt. And the correct answer is B, right? Let's move. Now we will discuss the most important aspect of this element capacitor, the energy stored in capacitor. Okay. So let's discuss energy stored in capacitor. We are assuming we have a parallel plate capacitor, or in fact you can take any kind of capacitor, no problem. Okay, but I am assuming as a reference as a parallel plate capacitor of capacitance C. Its two conductors have charges Q and minus Q, and the potential difference across the conductors is V. Okay, the Q, C and V are related as Q equals to CV according to definition, right? To find out what is the energy stored in this capacitor right now is, we will think of the process of charging this capacitor. Suppose initially there was no charge on the capacitor and we actually produced this charge by shifting Q charge from this plate to this plate, and if Q charge from this plate comes to this place, this becomes positive Q and this becomes negative Q. But suppose this was done in very small steps where a small charges like dq, dq, dq were transferred slowly. So in some intermediate stage, I can imagine this plate has charge small q, this plate has charge minus q, and another dq charge is being transferred. If this plate has charge Q and minus Q, the potential difference across the capacitor becomes Q by C. This is the potential difference. And dq charge is traveling. So you know work done in bringing a small charge dq across the potential difference Q by C would be potential difference times the charge dq, and this is the work done in bringing a charge dq from this plate to this plate slowly. If you integrate this work done, you will get the total work done in bringing the q charge from negative plate to positive plate. So we will have to integrate it from 0 to capital Q. And if you integrate this, you will get Q square divided by 2C. And this work done gets stored in capacitor as electrostatic energy. So electrostatic energy inside a capacitor is given by Q square by 2C. Okay, this is the first formula actually. If you replace Q by C times V, one C will get cancelled. Another formula becomes half C V square, right? And if you put 1 Q upon C as V, you will have another formula as half Q times V. But obviously, the first two are very common. The first two are very common. So commonly used formula are Q square by 2C or half CV square. Okay, just remember them. This is the energy stored. Let me tell you again. This is the energy stored in a capacitor having potential difference V, a charge on plate as Q and capacitance C. Okay, if you are given potential and capacitor, use half CV square as energy stored. If you have charge and capacitance, use Q square by 2C as energy stored, and if you have voltage and charge, use half QV as energy stored in capacitor. Okay, this energy is stored in this volume, and as in this volume electric field is almost uniform, this energy too is stored uniformly in this volume. So sometimes they ask us about energy density. And energy density is actually energy stored per unit volume. Okay, so let me write it somewhere. Energy density is actually energy stored per unit volume. Let me write VOL as volume, because if I write only V, you may confuse this with potential. So du by d volume is actually energy stored upon, right, volume. So let's write energy stored as half C V square divided by volume as area times gap. Okay, let me write the value of C. So we have half epsilon naught A by D, A, D and V square. You got A cancelled and the answer is half epsilon naught, and you know V by D as electric field. V upon D is electric field. So V square upon D square is square of electric field. So we have half of epsilon naught E square. This is the general formula for energy stored per unit volume in electrostatic field, or simply energy density. Listen again, we have derived it for a very special case, but believe me, this is a general formula and you can use it in any case you want. Okay, if at any point you know the electric field, the energy density at that point would be half epsilon naught E square, whether the electric field is uniform or non-uniform, whatever be the case. Okay, you can use this formula at a point. Okay, so let's see what we have next. Okay, so we have a question from NEET 21, and this says a parallel plate capacitor has a uniform electric field and the space between yes, it has a uniform electric field in the space between the plates. Okay, so if we have two plates, we have uniform electric field. Okay, the field is E. Next they are saying the distance between plate is D and area of plate is A. Okay, nice. The energy stored in the capacitor is, okay. So let me use the formula for energy stored as, they are not asking about energy density. They are saying what is the energy stored. Let me write half C is V square. Half CV square, remember half CV square. But you can write C as epsilon naught A by D. And V square as electric field square upon D square. Electric field square upon, no, the V is not electric field square upon D square. Actually, I've written it wrong. Actually, V is equal to integral E dot dr. So if you do integral E dot dr from here to here, you will have V square as E square times D square, right? So here 1D will be cancelled and you are left with half epsilon naught A E square D as energy stored in that capacitor. Okay, so next concept. What if we connect a capacitor to a cell or a battery? Actually, the basic method of charging a capacitor is to connect it across a battery. And if you connect it across a battery, the battery gives one plate a plus Q charge and other plate the minus Q charge. So let us understand the process of charging a capacitor. Okay. So suppose we have a parallel plate capacitor of capacitance C. C is obviously equal to epsilon naught A by D. And we connect it across a battery of EMF V with a switch. And when we close this switch, what happens? The moment we close this switch, the electrons of this plate are attracted towards positive potential of the battery. So electrons move in this direction. They gain energy and here they move. They are repelled by this negative terminal of the battery and they are repelled by this battery across this. So here we see deficiency of electrons and here we see excess of electron. So it starts gaining positive charge and it starts gaining negative charge. Okay. But remember the case of potentiometer. Here we have potential difference V and here we also seeing some potential difference developing. Okay. So as the charge keeps moving, the charges grow on capacitors, and when the charges grow, the potential difference also grows. And the moment potential difference across this becomes V equal to EMF of the battery, the flow of charge stops. Just like it is stopped in potentiometer and we got a null point. Here also we get null point and the current, the flow of charge ceases. Okay. So remember, when you close the switch, a current exists in the circuit for a small time interval. For a very small time interval, current exists in circuit, and very soon actually the potential across capacitor becomes equal to potential of the battery and the current stops. And when this happens, this is the final potential difference across capacitor. As this is the potential difference across capacitor equal to EMF of the battery, so potential difference times C gives you the charge plus CV on positive plate and charge on negative plate is minus CV. So always remember, when you connect a capacitor through a battery, the charge on capacitor plates is plus CV minus CV, where C is capacitance and V is EMF of the battery. The charge in the current in a steady state is 0, but initially some current flows. Okay, initially in fact very large current flows. Okay, also remember the current exists for few micro or maybe nanoseconds. Okay, for few, just imagine what is a micro. Micro is 10 lakhs times smaller than a second. So the current that you are seeing, the flow of charge that you see in the circuit exists for only few microseconds or few nanoseconds. And almost instantly when you close the switch, the capacitor gets fully charged. So steady state, this is called a steady state. When it is fully charged, we call it a steady state. So in a steady state, there is no current in this capacitor, only it has some initial current, right? So the charge on capacitor is charge on capacitor. Q is CV, where C is capacitance, V is EMF of the battery. Okay, the energy in capacitor, energy stored, U equals half C V square. And can you see, initially the batteries, the plates were uncharged. Initially the plates were uncharged, they had no charge, and now this plate has plus CV charge, so definitely the battery has given it a charge equal to CV. The battery has provided a charge CV, and when battery provides charge to circuit, it does work. So let me write work done by battery, work done by cell or battery equals, actually work done by cell equals the charge provided by battery multiplied by EMF of the battery. So it is actually equal to CV square, CV square. But there is a miscalculation, or there is a problem. Battery does work equal to CV square, and the energy stored is only half CV square. Where gone the half CV square? Because battery is doing plus CV, 1 CV square, and only half of it is being stored. The remaining is actually destroyed. The remaining is actually converted into a heat loss that occurred because of this instantaneous flow of large charge. Okay. So actually you can say the work done by battery is equal to energy stored in the by obviously conservation of energy, the work done by battery is equal to the energy stored in the capacitor and plus heat loss. The delta H represents heat loss. So if you want to know what is the heat loss delta H, that would be equal to work done by the battery minus delta U, and it is equal to CV square minus half CV square equals to half CV square. Remember, actually many students make a mistake. They remember this point that heat loss is equal to energy stored by the capacitor, or it is equal to half of the work done by the cell. This is true in this specific case only, but this is not true everywhere. So you should not make any conclusion like this. Okay. Whenever you are asked to find heat loss, just calculate the energy stored in the capacitor or the change in energy of the capacitor. Calculate work done by the battery and minus work done by the battery minus change in energy of the capacitor will give you heat loss. Always do it conceptually, right? One more and very important type of question that we see everywhere in NEET and JEE, that if a charged capacitor is connected to another charged capacitor or an uncharged capacitor. So if one capacitor or two capacitors which are both charged or any one of them charged, and they are connected to each other, okay, and they say, or they want you to calculate what is the final potential difference across them, what is the final charge on them, what is the heat loss in them, what is the initial and final energy stored on them. If they ask you the question like this and they connect two capacitors, one or both charged, then how you have to proceed in that question, let us see here. So here we have two capacitors, C1 and C2. The C1 is charged to a potential difference V1 and C2 is charged to a potential difference V2, and they are connected but switch is open. And as as long as switch is open, no charge can flow in the circuit. Charge can flow anywhere in the circuit only when switch is closed. Remember this point. Without closing the switch, the charge cannot flow. The charge needs a complete loop to flow. How these are charged? Actually, these are capacitors C1 and C2 are separately charged by separate batteries of EMF V1 and V2, and now they brought and connected to each other like this. So if you connect two batteries, there can be two cases. There can be two cases. The first case is positive and positive of, or you can say positive plate and positive plates are connected to each other, negative and negative plates are connected to each other. This is first case. And the second case becomes positive plate of one and negative plate of other are connected to each other. So let us discuss first the case 1. When same polarity connected means positive plate of one is connected to positive plate of other. Okay. If you do so, just try to imagine if I take this as one system. Obviously, this plate is connected to this plate by this conducting wire, but the charge cannot go on right hand side because there is a air gap or there is some insulation between the capacitor plates. So charge will remain on the left side. Its charge can go to this plate, this charge can go to upper plate, but the charge will remain on left side. On upper plate we had plus, on upper plate we had plus C1 V1 charge, and here we had plus C2 V2 charge. Here we had minus C1 V1 charge and minus C2 V2 charge. So total charge on the left hand side is C1 V1 plus C2 V2. Okay, C1 V1 plus C2 V2. But when I close this, okay, let us see in the next problem. Next, if I close this, okay, if I close this, what happens? Actually, these two plates are connected and these two plates are connected. So finally, the potential difference on the two capacitors will be equal because potential of this plate will be same as, yes, potential of this plate will be same as this plate because of this wire, and potential of this plate will be same as this plate because of the wire. So potential difference across this capacitor and potential difference across this capacitor must be same. So let us assume the final potential difference across them as VF and VF. Across both, the potential difference will be same. So the charge on left plates combined would now becomes C1 VF equals, C1 VF plus C2 VF. But as you know, the charge on left hand side will remain conserved. It cannot go on the right hand side. So charge on left hand side has to remain constant. So charge on left side was C1 V1 plus C2 V2, and now it is CF VF plus C2 VF. So I can say the initial charge on left hand side is still the same. So C1 V1 plus C2 V2 is same as C1 VF plus C2 VF. So from this we can write VF as C1 V1 plus C2 V2 upon C1 plus C2. Okay, this is the result, or you can say the final potential difference. Actually, this mathematics is very similar to, mathematically similar to a case of inelastic collision between two masses M1 and M2. So let me tell you, there is no conceptual, you can say, relation between the two. It is only mathematical relation. So let me tell you the analogy. You have to put mass in place of capacitance and velocity in place of voltages. Okay. And as you know, when these two masses make an inelastic collision means finally they move with same velocity. Okay. So whenever they make an elastic collision, you know the linear momentum is conserved. Remember, the linear momentum is conserved. So if you write linear momentum here, it will be m1 v1 plus m2 v2. See, we have masses at the place of capacitances. We have velocities at the place of voltages. Try to remember this, masses at the place of capacitance and velocities at the place of voltages. And finally, after collision, when the two masses move together with a common final velocity, the momentum becomes m1 plus m2 times v final. Okay. And as momentum is conserved, initial momentum m1 v1 plus m2 v2 equals m1 plus m2 times vf, v final. So v final becomes m1 v1 plus m2 v2 divided by m1 plus m2. So you can also think of the two capacitors when both positive plates connected together, negative plates connected together, means when same polarity are connected together. You can assume these two capacitors as two moving masses in same direction with velocities v1 and v2. Replace mass by capacitance or capacitance by mass, velocity by voltage or voltage by velocity. And if you, by conservation of momentum, write final velocity, this is the final velocity. The final voltage can be found by replacing masses by capacitors and velocity by voltages in the final result. But still for this is not a very good approach. But what if you are asked to find the heat loss or the loss of energy? So for calculating the loss of energy, you will have to calculate the initial total energy. Let me just say it once. The energy stored here is half C1 V1 square. The energy stored here is half C2 V2 square. The sum will be initial energy. The final energy would be half C1 V final square plus half C2 V final square, and by putting this value of V final, you will get total final energy. And when you subtract initial energy minus final energy, you get the heat loss. This is a very big process and involves a lot of calculations. But this result, the result that we obtain, will be in front of you if you use this analogy. I think you remember in these type of collisions, the heat loss or the loss of kinetic energy, I must say, the loss of kinetic energy used to be K loss, used to be half mu V relative square, half mu V relative square, where 1 by 2 is 1 by 2, mu is m1 m2 divided by m1 plus m2, and V relative, let us check, V relative is V1 minus V2. As you have to square it, it doesn't matter. You do V1 minus V2 square or you do V2 minus V1 square, it doesn't matter. This is the loss of kinetic energy. By looking at this formula, you can write the heat loss in this process. Let us write heat loss. Heat loss. The formula for heat loss can be written as 1 by 2. Replace masses by capacitors. Remember, masses by capacitors. So I'll write C1 C2 divided by C1 plus C2. And velocities by voltages. So if same polarity is connected, positive is connected, it means the two masses are moving in same direction. And relative velocity becomes V1 minus V2. So relative potential difference becomes V1 minus V2 whole square. That is the heat loss. Just remember this formula by remembering this small formula as half mu V relative squared. Okay. Okay. So before jumping into problems, let us understand this. It's second case. When opposite polarities are connected. When opposite polarities are connected, here we connect positive plate to negative plate and positive plate to negative plate. So if you look at left side, now the total charge that will remain conserved is C1 V1, positive C1 V1, negative C2 V2. This is the charge on the left side. And when you connect, or you can say when you close the switch like this, the charge on the left side now becomes, obviously now the potential difference will be same. So the potential difference, charge on left side now becomes C1 V final plus C2 V final. But this is the charge after closing the switch. It will be equal to the charge before closing the switch on the left side. So it was C1 V1 minus C2 V2. So V final becomes C1 V1 minus C2 V2 divided by C1 plus C2. But this process you can again compare with collision of two masses, but as the different polarities are connected, you have to take the two masses moving in opposite directions. And if the masses are moving in opposite directions, the momentum becomes m1 v1 minus m2 v2. And after collision, the momentum becomes m1 plus m2 times final velocity. And initial momentum, let's write m1 v1 minus m2 v2. And you can see the final potential becomes, final velocity becomes m1 v1 minus m2 v2 divided by m1 plus m2. Obviously, by replacing masses by capacitances and velocities by voltages, you can know the final voltage just by looking at the formula for final velocity. But the bigger advantages come when we talk about heat loss. As you know, the loss of kinetic energy, its formula is half mu V relative square. So here heat loss would be equal to 1 by 2. As you know, mu is m1 m2 upon m1 plus m2. Replace mass by capacitances. We have C1 C2 divided by C1 plus C2. And now relative velocity. Relative velocity becomes relative potential here. But as you know, this is similar to the two masses moving in opposite direction. So here relative velocity becomes V1 plus V2. So again, here also the relative potential will become V1 plus V2. So here we will have V1 plus V2 square. And you calculate this, you will have the formula for heat loss. Okay. So I think you got this point. Let us solve. So now we have a problem, and the problem says a capacitor is charged by a battery, and the battery is removed and another identical uncharged capacitor is connected in parallel. So let me draw the diagram. We have a capacitance C and it is charged to a potential of V with the battery, and now we have connected another identical but uncharged capacitor across this. If we want to calculate the heat loss So let me just write the initial energy. Okay, initially this capacitor has no energy and this capacitor has U initial as half CV square. Okay, and when these two are connected like this, they achieve a common potential. The common potential can be found by comparing this to a collision of two masses. One mass has mass m, velocity v, and another mass has mass m and with zero velocity, as there is no potential drop across it. But as we have to just find the heat loss, so let me write directly heat loss, and heat loss will be written as half mu v relative square. At the place of mu, I'll write C1 C2, that is Cc upon C plus C times v relative. So you know the velocities are related to or are analogous to voltages. So one capacitor has voltage V, another capacitor has voltage 0. So relative potential is simply V minus 0, that is V square. So it becomes half, no, it becomes 1 by 4 CV square. This is the heat loss. So if initially we have 0.5 CV square, the lost energy is 0.25 CV square, the remaining energy would be this minus this, that is 0.25 CV square or 1/4 of CV square. So the remaining energy would be U final, it will be U initial minus heat loss, and it will be 1 by 4 CV square. So obviously the energy of resulting system decreases by a factor of 2. Okay, you can see. Okay, next question. Here we have a capacitor. This was asked in JEE also once. Okay, so I have not taken that question because the both are almost same. So here we have a capacitor of 2 microfarad charge is charged by this battery of voltage V. When the switch is shifted from 1 to position 2, the percentage of stored energy dissipated. They are asking us what is the percentage of stored energy dissipated. Okay, so let us find the initial energy. The initial energy is only in this capacitor 2 microfarad, and this capacitor had zero energy because there is no potential difference. So initial energy is half C is 2 microfarad, V square, so it becomes V square microjoule. And when it is connected, when switch's shift is on position 1, the potential difference across this capacitor is also V. Okay, but when the switch is shifted to position 2, here we have connected one charged capacitor and one uncharged capacitor. Let us directly write what is the heat loss. So heat loss from the formula half mu V relative square, I can write half mu, I can write as C1 C2 upon C1 plus C2, that is 2 times 8 upon 2 plus 8, which is 10 microfarad, times V relative square. So here we have voltage as V, here we have 0, so relative voltage is V, so V square as V square, and let us see what we have. We have 0.8 V square. Okay, so you can see the initial energy is V square and heat loss is 0.8 V square. So it is 0.8 fraction, the heat loss is 0.8 fraction of initial energy, that says 80% energy has been lost. So correct answer is C. Okay, isn't this simple? Always use the collision analogy. Okay, let us use in some more problems. So in this question we have two capacitors of capacitances C and 2C and potential differences V and 2V. Let us see. One capacitor, capacitance C, another capacitor, capacitance 2C, voltages V and 2V. They are then connected in parallel in such a manner that positive of one is connected to negative of other. Okay, so suppose this is positive, this is negative, this is negative, this is positive, and positive of one is connected to negative of other. negative of one is connected to positive of other, but they will be connected when switch will be closed. Okay. Now they are asking us the final energy of this configuration. What will be final energy of this configuration? So obviously our approach would be, first we will calculate the initial energy, then I'll calculate the loss, and initial energy minus loss will be obviously the final energy. So let us find the initial energy. The first capacitor C, voltage is V, so energy is half CV square, that is 0.5 CV square, plus the second capacitor of capacitance 2C, voltage 2V, so we have half 2C and 2V square, 2V whole square, and here on totaling we will have 4.5 CV square. This is the initial energy, right? Now we have to calculate heat loss. Heat loss. The formula for heat loss is 1 by 2 C1 C2 C2C divided by C1 plus C2, that is 3C, multiplied by relative voltage square. But as you know, the positive of one is connected to negative of other. This will be compared with two masses moving in opposite direction, where relative velocity becomes V1 plus V2. So here relative potential will become V1 plus V2, that is 3V. So relative potential square, that is 3V square. And let us calculate what is the answer. Answer is 3 CV square. So if initially we had 4.5 CV square and the loss is 3 CV square, the remaining energy would be 1.5 CV square or 3 by 2 CV square. So correct answer is D, 3 by 2 CV square, right? Okay. So let us move to next question. Okay. Can you see in every problem we are using the same formula, and this concept is very, very important for capacitor. Okay. In every exam, whether it is NEET or JEE, doesn't matter. A 60 picofarad capacitor is fully charged by 20 volt supply. So again, let us see. Let's have 60 picofarad capacitor and charged to 20 volt. Okay. It is then disconnected from the supply and is connected to another uncharged capacitor. Okay. So we brought this capacitor from supply and we connected it to another uncharged capacitor of 60 picofarad in parallel. The electrostatic energy that is lost, they are directly asking us what is the loss of energy. So let us write loss, delta H equals to half C1 C2 upon C1 plus C2 will give you 60 times 60, that is 60 square upon 60 plus 60, that is 120 times relative potential difference. One has potential 20, one has 0. So relative potential is 20 actually, 20 square. Let us see what we have as an answer. So we have 60 square as 60 multiplied by 60 divided by 2 times 120 multiplied by 400. So let's see, we have by 2 to 100 and it is equal to 6000 picojoule, and 6000 picojoule will be equal to 6 nanojoule. So correct answer is 6, right? Over to next question. Here we see a capacitor is fully charged with voltage V0. After disconnecting the voltage source, it is connected in parallel with another voltage source. Another uncharged capacitor of capacitance C by 2. So we have a capacitor C charged to potential V0 and it is connected to another capacitor C by 2. Okay. And now they are asking, what is the energy loss? Just calculate. We have the formula. The energy loss is equal to half C1 C2 C by 2 upon C plus C by 2. multiplied by relative potential, that is V naught square. So the answer would be, I think C by 2 upon 3C by 2. So we have CV naught square by 6. And correct answer is D. It is exactly identical as the last problem. Next question. I think you all can calculate it yourself. Just solve it yourself and then look for solution. So here we have a 10 microfarad capacitor fully charged to potential difference 50 volt. After removing the voltage source connected to uncharged capacitor in parallel, now the potential difference across them becomes 20 volt. And what is the capacitance of the second capacitor? So we have one capacitor as 10 microfarad and it is charged to 50 volt. Another capacitor, let's say C, and now when they are connected, the final voltage becomes 20 volt. As you know, this is similar to a case of collision where one ball having some velocity is going to collide inelastically with a ball having some mass C having no velocity. So by conservation of charge, or by analogy you take case of conservation of momentum, let us solve it basically by conservation of charge. The left hand side's charge initially is 10 microfarad times 50. The lower charge is 0 equals, let us say the final voltage, or actually we are given that final voltage is 20. So finally the charge becomes 10 plus C times 20. So here we see C plus 10 is equal to 25. So C will be simply 15 microfarad, and the correct answer is obviously A. Okay, next question. Now we will learn how to apply KVL and KCL, that is Kirchhoff laws, in circuits having capacitors. Okay, so this is the part of a circuit, right? And we have a resistance, capacitance and batteries, all three. So the first point that comes to our mind is to mark polarities. So as you know, in the direction of current, in resistor, in the direction of current, potential decreases. So I can mark positive and negative sign like this. Okay, because potential is decreasing in the direction of current. In capacitors, you are already given charges. So positive charge plate is positive and negative charge plate is negative. And in battery, always the bigger line is positive and the smaller line is negative. Now, if you want to write KVL in circuits involving capacitors, I'll write KVL from A to B. So I'll start with VA, that is potential at A, and then I am moving from A to B. So first I found resistance, and in resistance you know the drop of potential is I times R, and as we are moving towards right and potential is decreasing, I'll write minus I times R. Okay, then I have capacitor. You know, for capacitor, Q equals CV, so V equals Q by C, right? Q, V, that is potential difference across capacitor, is Q by C, okay? But can you see, from positive to negative, if you go from positive to negative, the potential will drop. So I will write minus potential difference across capacitor, and that is actually Q divided by C. This is the way we write potential difference across capacitor in KVL. And then we have a battery. So battery, again we are going from positive to negative, so potential will drop, and I'll write minus V, and V reached B, so I'll write VB. So this is the way we write KVL in capacitor circuits, right? If you apply KVL in a loop and you start from a point and end at that point, there is no need to write VA and VB because the both points are same and they will be cancelled. So I'll simply write the potential drop or rise of every element and make it equal to 0. Okay, so I think you got the idea. Just you have to write KVL or KCL similar to the way or the manner we learned in last chapter. That is correct. Now it is time for KCL in capacitor circuits. So suppose you have a junction or a node and the potential of these 3 points are V1, V2 and V3, and suppose you want to find potential at this junction. So let us assume this potential to be X, right? Now look, the 3 plates of 3 capacitors are connected to this point. Which one? This plate and this plate. These 3 plates of 3 capacitors are connected at this junction. So if you take a system of these 3 plates, you will notice that this system is actually electrically isolated from the rest of the network, because the charge cannot go from here to here, the charge cannot go from here to here, and the charge cannot go from here to here. So if there will be some changes, there will be some changes in the circuit, the net charge of these 3 plates will remain conserved, because the charge cannot come on this system of 3 plates and the charge cannot go from the system of these 3 plates of capacitors, right? So suppose the charge on this is say Q1, the charge on this is say Q3, and the charge on this plate is Q2. I'll write Q1 plus Q2 plus Q3 must remain constant. Okay. If in circuits it is not specified that few capacitors had some initial charge, then we assume all capacitors to be uncharged initially. And if all these capacitors were uncharged initially, obviously the sum of these 3 charges must be 0 initially. And if it is 0 initially, it will remain 0 for all the time, right? So you can say the Q1 plus Q2 plus Q3 will remain 0, okay, will remain 0 if it is not specified that few capacitors had initial charge in the beginning of the circuit. Okay, so now if you want to write these charges, the idea is simple. The idea is the Q equals C times potential difference. Okay, so assuming this plate to be positive, I'll write the potential difference across this will be X minus V1. So potential difference will be X minus V1 times C. This is the value of Q1 because Q is C times V. The Q2 can be written as X minus V2 multiplied by C. Sorry, it is C1, it is C2, and plus Q3 can be written as X minus V3 times C3, and this sum equals to 0 if there is no charge initially on any of the capacitor, right? Okay, so remember this law. The charge on all plates connected to a node will remain same. There is one more and very important point according to the trend of problems coming in front of you, and it is the RC circuit in a steady state. What are RC circuits? RC circuits are simple circuits having some battery and resistances and having capacitances also. So if a circuit contains resistance, capacitance and battery, we call them RC circuits. Okay, so the idea is how RC circuits behave in steady state. So what is a steady state? A steady state is a state when all the parameters of circuit are constant. Means the current is constant, the charge is constant, the potential differences are constant, then we say the circuit is in a steady state. Okay. So suppose this is the circuit, this is the branch of a circuit, and on the left and right point of the branch, the potentials are 6 volt and 2 volt, right? 6 volt and 2 volt. I'm taking a numerical example, right? And the capacitance is 3 microcoulomb. Sorry, it must be 3 microfarad. Yes, the capacitance is of 3 microfarad. Okay. And if this circuit or part of circuit is in a steady state, all the parameters will be constant. So suppose the charge on the capacitor is Q and minus Q, and it is given that the circuit is in a steady state. Obviously, the charges on the two plates must be constant. And if the charges are constant, you can write dq by dt will be 0, because in a steady state, Q is constant. And you already know dq by dt is current. So it says current is 0. Current is 0. So always remember, if a circuit, if a RC circuit is in a steady state, then the branch having capacitor, cannot have any current. The current in the branch having capacitor will be 0, because if there is current, the charge will change, and if charge changes, we will not say the circuit is in a steady state. So always remember this, in a steady state, when charge on capacitor is constant, the rate of change of charge, that is current, in the branch having capacitor is always 0. Okay, so remember this point, and this is again I'm saying it's a very important point according to questions. Okay, so let us solve few problems, obviously very important problems asked previously. Okay, so we have a combination of capacitors. Okay, and can you see here we have a 8 volt battery, 2 microfarad capacitor, 4 microfarad, 3 microfarad and 9 microfarad. Okay, and they are asking us the combination of capacitor is set up as shown in figure. The magnitude of electric field due to point charge Q. Okay, we have to find the magnitude of electric field due to point charge Q. And what is Q? The Q is actually the charge equal to the sum of charges on 4 microfarad and 9 microfarad. So this Q is actually the sum of charges on 4 microfarad and 9 microfarad. Okay, so we have to find the charges on 4 microfarad and 9 microfarad. Okay, and then when we find the charges on these two, we have to sum them. That is equal to Q, and we have to find the electric field because of this Q at a distance of 30 meter from it. Okay, so let's move to circuit. Okay, see in this circuit, can you see the 3 microfarad and 9 microfarad? Okay, they are in parallel. They are in parallel. Okay. And if they are in parallel, obviously the potential difference across these two will be same. Just focus, just try to focus on 3 microfarad and 9 microfarad. If these two are in parallel, the potential difference across the two must be same. And if potential difference across two must be same, okay, so in capacitors you write potential as Q by C. For these two, potential is same. So Q by C is constant. And if Q by C is constant, you can always write Q is proportional to C. Means on bigger capacitors, the charge will be bigger, and on the smaller capacitor, the charge will be smaller. So let us use this fact to decide the charges on these two. As charge is proportional to capacitance, I can assume the charge on 3 microfarad to be 3Q and charge on 9 microfarad to be 9Q. Okay, I can assume it like this because if these are the charges, Q by C is constant for these two. Okay, if the charge on here 3Q and 9q. Obviously, it must have gone there through this path. So 3 plus 9 is 12. So 12q has been passed through this line. So on this plate, the charge should be 12q. Okay. And now I can apply a KVL equation in any one branch to find the value of charge. So suppose I take this as a loop, right? This as a loop to apply KVL. Let us apply KVL. I'll start from here and will end at this point, and I'll move according to this direction. So first I have battery, and if I move from here to here, the potential increases by 8 volts. So I'll write 8 volt. Let's not write unit, just write the values 8. Then I cross this capacitor because there is nothing till this point. Then I cross this capacitor, and if I cross this capacitor in this direction, obviously potential is going to decrease. Okay. Why potential is going to decrease? Because positive terminal of battery will give it positive charge. So this plate will be positive and this will be negative. So potential will decrease, and potential in capacitor is written as Q by C. So we have 12Q divided by 4 microfarad. Remember, if here we have microfarad, the charge 2 should be in microcoulomb, so that the micro can be cancelled. Then I have this 3Q charge on 3 microfarad. So I'll write minus 3Q divided by 3 microfarad and equals to, we returned to the same point. So we will write 0. Okay. And now on solving this, you will get 8 minus 3Q minus Q, that is 8 equals 4Q, and this gives you Q equals 2 microcoulomb. If Q equals to 2 microcoulomb, the charge on this capacitor would be 12 multiplied by Q, that is 24 microcoulomb, and the charge on 9 microfarad would be 9 times Q, that is 18 microcoulomb. So the total charge of these two capacitors will be 12Q plus 9Q, that is 21Q. Okay, 21Q. The Q can be written as 21Q, and putting the Q as 2 microcoulomb, it will be 42 microcoulomb. Right? And since we have to find the field because of this charge at a distance of 30 meters from it, okay, I'll write the electric field as K, which is 9 times 10 to the power 9, times Q. Q is 42 times 10 to the power minus 6, divided by R square. And what is R square? R is 30, so we have 30 multiplied by 30. Okay, and solve this and you will get 420 newtons per coulomb. So obviously the correct answer is B. Okay, I think you got this idea, and let's move to next question. Again, this is again a very interesting question, and here say we are given this circuit, and in this circuit they are asking us what is the charge on 5 microfarad capacitor. This is the 5 microfarad capacitor. Let us see, and we have to guess the charge on this capacitor. Again, let us assume the potential of this point to be 0. I think you remember we have a freedom to choose potential of one point as 0 in any circuit. So I'll assume potential of this point is 0. If potential of this point is 0, move in this direction, and you're crossing this battery. So potential at this point would be 6 volt. Similarly, potential at this point would be 6 volt, right? And here, let us assume potential is X. And now I will apply KCL at point X. I think you all remember the charge on these 3 plates will remain constant. And as these capacitors had no charge initially before this system was on, before the circuit was set up, the three plates total charge would be 0 because they had no initial charge. So the net charge is 0 on these three plates. So it will remain always 0 as this system of three plates is not connected to rest of the network. So let us write the total charge on these three plates, and the charge becomes x minus 6 potential difference times capacitance, that is 2, plus x minus 6 times capacitance, which is 4, plus x minus 0, that is x, times capacitance, that is 5, and equals to 0. That is KCL equation at that node. And let us solve this. 2x, 4x, 5x, that is 11x equals 12 plus 24, that is 36. So x equals 36 divided by 11. This is the potential at this point. And if you know potential at this point, x, here we have potential 0. So potential difference across 5 microfarad is actually x. And if potential difference is x, the charge on 5 microfarad, is going to be C times V, that is 5 times potential difference is 36 by 11 microcoulomb. Okay. And if you solve this, that will be 180 by 11, and 180 by 11 will be nearly 16.36 after solving. Okay. So again, a very simple question. Let's move to next one. Okay. It is similar to the question that we solved few minutes back. In this question, they are saying in the circuit shown in figure, the total charge is 750 microcoulomb. Means from the battery, the total charge that is flowing in the circuit is 750 microcoulomb. So on this capacitor, the total charge will pass like this, 750 microcoulomb, and then it will split into two, right? So the sum of charge on these two capacitors would be 750 microcoulomb. Okay. Now they are saying the potential difference across capacitor C2 is 20 volt, right? Here potential difference is 20 volt, and these two are in parallel. So if here potential difference is 20 volt, here too the potential difference will be 20 volt. So I can say across C3 potential difference is 20 volt. So let us find charge in C3, and in C3 the charge would be Q will be C times V. C is 8 microfarad and potential difference is 20 volt. This becomes 160 microcoulomb. And if charge on this plate is 160 microcoulomb, the charge on this would be the total charge 750 minus 160. So the charge on C2 would be 750 minus 160, that is 590 microcoulomb. So correct answer is B. Okay. I hope you are learning this session, and I'll again say for better learning, you watch this entire episode, or you can say the lecture, in parts of say 1 hour each, not more than this, and practice these questions yourself without looking at solution, and then it will be very beneficial for you. Okay. So this question is actually based on the concept of a steady state. Okay. And they say find the charge in a steady state of the capacitor. So if capacitor is in a steady state, right, the capacitor is in a steady state, the charge on capacitor will be constant. Let us say plus Q and minus Q. And in this branch of capacitor, the current would be 0. But current is 0 only in the branch containing capacitor. If current has a way to move, if current has a loop to move in, the current will obviously flow. So current here will flow obviously after opening the switch, after closing the switch in fact. So current can move in this path. So if a closed path is available for current, it will definitely move. And see, this path is available. If this path is available, current I will go here, 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 and from here the current going towards this direction is 0. So the total current I will come in this path. So if you want to calculate current, the current would be equal to the EMF 12 divided by the total resistance, that is 300 ohm, and I think the current would be 0.04 ampere. This is the value of current in the circuit. Okay, now see, if this is the value of current in the circuit, the potential difference across this resistance I can find, and potential difference across this 200 ohm resistance would be, potential difference across 200 ohm would be current times resistance, and the current times resistance would be 0.04 times 200, that is 8 volt. And why I am trying to find potential difference across this resistance? The reason is simple, because this resistance is in parallel with this capacitor. And if this resistance, this capacitor are in parallel, the potential difference across the two will be same. So you can say the potential difference across the capacitor is also 8 volt. Okay, and if potential difference across this capacitor is 8 volt, the charge on that capacitor, the charge on 1 microfarad capacitor can be written as C times V, that is 1 microfarad multiplied by 8 volt. It becomes, it is 1 microfarad into 8 volt, it becomes in fact 8 microcoulomb. Actually, no answer is matching, right? That's why this question was a bonus. Okay, so the correct answer is none of these. Okay, so let us move a little and solve this interesting problem. Okay, in this question again they say, in the given circuit diagram, when current reaches a steady state, listen carefully, the current is in a steady state. Obviously the circuit is in a steady state, because when current reaches steady state, everything will reach a steady state. So if current reaches a steady state in the circuit, what they are asking us, what is the charge on the capacitor? What is the charge on the capacitor? Just listen carefully. In a steady state, obviously the current here is 0. Means current is 0 in the branch having capacitor. So obviously this branch there is no current, but current has a path to move, because this path is available for current. This path is available, and if this path is available, the current will flow, and the value of current can be written as, the current can be written as EMF divided by net resistance of the path, and that is R plus R2. R plus R2. This is the current. Okay. Okay. Now, if you now know the current in this circuit, actually the potential difference across R2. Can you write potential difference across R2? See, potential difference across R2 would be equal to, actually, the current in this R2 multiplied by R2, that is IR2, and IR2 will be equal to E divided by R plus R2 times R2. Just try to imagine, we have found the potential difference across this resistance, and since this resistance is in parallel with this resistance, this combination of R1 and C, we can say the same potential difference is across this capacitor and R1 combination. the same potential difference is across this capacitor and R1 combination. So here also potential difference is V. Now if current in this branch is 0, obviously the potential difference across R1 is 0, because current in R1 is 0 in a steady state. So if potential difference across R1 is 0, the entire potential difference is across the capacitor. So entire potential difference is across the capacitor. So across the capacitor, you can say potential difference is this. This is also the potential difference across capacitor. And if this is the potential difference across capacitor, the charge on the capacitor can be written as C times V, which will be CE R2 divided by R plus R2. And the correct answer is obviously D. Okay, over to next question. Okay, we have theory now. So we have to learn now the series combination of capacitors. So if few capacitors are arranged in series, that is they are connected side by side. Let us say these capacitances are C1, C2, C3. But remember one point. These three capacitors are said to be in series combination only if all three capacitors have equal charge. Only if all three capacitors have equal charge. Means if this capacitor has charge Q and minus Q, this too must have Q and minus Q, this too must have Q and minus Q. Suppose few of them or all of them have some initial charge and then they are connected in series. Or let me clarify, suppose all of them had some initial charge and unequal initial charge, and then when you connect these three in series or in this combination, the charge on them will never be same again. If the charges are initially unequal, the charges will never be same, and if charges are never same, they will not be called in series combination. So series combination has a condition here. And what's the condition? The charges must be same. And that can be true in two conditions. The first, if all three capacitors are initially uncharged. Say if all three capacitors are initially uncharged, then suppose the Q charge is flowing in this branch. Obviously the same Q charge will flow in this branch. The same Q charge flow in this wire, and if Q is flowing, the charge on this plate will be Q minus Q, Q minus Q, and Q is flowing here, so Q minus Q. So the three charges will be same. The charges on the capacitor will be same if they have no charge initially or they have equal charge initially. If they have unequal charge initially, they will not be called in series. So remember this point. The series combination has a condition. So if all capacitors have same charge, this is possible if initial charge is 0 or same. Okay, we say the capacitors are in series combination. Okay, so remember this point. Okay, when we call them as series as in series combination, obviously the net capacitance is given by 1 upon C net equals to 1 upon C1 plus 1 upon C2 plus 1 upon C3. The similar formula we used for resistances in parallel, but here we use this type of formula in series. Remember this point. And division of voltage. Okay, so here we see the voltage is divided. Here, the voltage is divided. So you apply a V voltage across these three. So the V will be divided into three parts: V1, V2, V3. Right. So V1 plus V2 plus V3 would be equal to the total voltage V. So we see the division of voltage and same charge on each capacitor. Okay. So that is the point of series combination of capacitors. Parallel combination of capacitors. That is simple actually. You know, if three capacitors C1, C2 and C3 are in parallel, they all have same potential difference. They all have same potential difference. So potential difference is same. Division of charge means if charge goes from here, let Q, it will be splitted into three parts. Let's say Q1, Q2 and Q3. Okay. And division of charge is according to Q proportional to C. How? You know, as potential is same and potential is written as Q by C. Q by C. So if potential is same, you can write Q by C as constant. And if Q by C is constant, Q will be proportional to C. I think I explained this point initial few questions back also. So obviously if Q is proportional to C, the bigger capacitor will have bigger charge, the smaller capacitor will have a smaller charge. Okay. And the C net in this case, the net capacitance of these three capacitors will be given by C1 plus C2 plus C3. And if there are more capacitors connected in parallel, you will have to C4, C5, similar to the case of series combination of resistance, right? Okay. So these were two combination of circuits, capacitors. Always remember, in parallel combination, the idea is very simple. In parallel combination, the potential difference is same. But the series combination has a condition. So the 3 or 4 or 5 capacitors will be called in series combination, and this formula will be valid only if initially they have either zero charge or same charge. Only in that case, in any state of the circuit, that all three or all of them will have same charge always. Okay. So let us solve few problems based on this. Okay. Remember this point, that the formula we use, with the similar formula we use for series combination, the similar formula is used here for parallel combination of capacitors. And the type of formula we were using for parallel combination of resistances, we use similar formula for series combination of capacitances. So the mathematics is a little opposite to each other. Remaining all things are valid. Means the type of symmetry we studied in last chapter, the all type of symmetry are valid here. The condition of Wheatstone bridge, the similar condition of Wheatstone bridge is valid here also. Okay, so let us see what we have next. So we have to question, and it says two equal capacitors are first connected in series. So if two equal capacitors are connected in series, let's say C and C, the C net would be, so 1 upon C net is going to be 1 upon C plus 1 upon C. So C net will be C by 2. I feel you should remember this point here also, that if n capacitors, n identical capacitors are connected in series, then the net capacitance would be C by n. So if two capacitors are in series, the net would be C by 2. For two capacitors, for only two capacitors, C net is also written as C1 C2 divided by C1 plus C2. So remember this point. Okay. So C net in series case is C by 2, and if you connect them in parallel, so if you connect them in parallel, the C net dash, it is C net C by 2 and C net dash. C net dash means when we are connected them in parallel. In parallel we have formula as C1 plus C2. So in parallel the net capacitance is going to be 2C. And we have to find ratio of these two equivalent capacitances. So obviously C net divided by C net dash is equal to C by 2 divided by 2C. This is 1 by 4. So correct answer is obviously B. Okay, over to next question. Here we have effective capacitance of parallel combination of two capacitors is 10 microfarad. It is actually 10 microfarad, right? So we have two capacitances, C1 and C2, and their net capacitance in case of parallel combination is 10 microfarad. So I think I can write C1 plus C2 as 10 microfarad. Okay, now they say if these capacitors are individually connected to a voltage source of 1 volt, means if these two capacitors have equal potential difference of 1 volt, the energy stored in C2 is 4 times that of C1. Okay, it means as I think you remember, the energy stored formula is half CV square. So energy stored in C2 is half C2 1 volt square is actually 4 times half C1 1 volt square. You cancel everything and you will see C2 is 4 times C1. Okay, and if C2 is 4 times C1, I think the solution is very clear. You can solve these two equations, or I can simply say C1 equals 2 microfarad and C2 equals 8 microfarad. Then only the sum is going to be 10, and C2 is 4 times equal to C1. So obviously these are the values of C1 and C2. Now they say if these capacitors are connected in series, their effective capacitance would be. So now if these two are connected in series, the effective capacitance by the formula C1 C2 upon C1 plus C2 can be 2 times 8 upon 2 plus 8, that is 1.6 microfarad. So the correct answer is C. Okay. Next question. Now we have 7 capacitors, each of capacitance 2 microfarad, and they are to be connected in a special configuration to obtain an effective capacitance of 6 by 13 microfarad. So 7 capacitors, each of 2 microfarad, and they are connected in a special configuration so that we can have an effective capacitance of 6 by 13 microfarad. We have to answer which one is the correct configuration. I'll try this by simple hit and trial method. I'll pick A and see if 5 are connected in parallel, their combination becomes 5C, and these two are in series, so their combination becomes 2C, and this 5C and 2C are in series. This 5C and 2C are in series, so I can write 5 multiplied by 2 divided by 5 plus 2. I get 10 by 7, and this is not the answer, so I can cancel this. Let's try this. These 3 capacitors have an effective capacitance of 2 multiplied by 3, that is 6 microfarad, and these 4 are in series, so these 4's net would be 2 by 4, that is 0.5 microfarad, and these two combinations are in series. Can you see that? So if you solve 6 multiplied by 0.5 divided by the sum of these two, 6.5, we will have, yes, 6 by 13. Okay, so obviously the option B is correct. Okay, we don't have to check for other options. Okay, over to next question. 3 capacitors, each of 4 microfarad, are to be connected in such a way that effective capacitance is 6 microfarad. So we have 3 capacitors and each are of 4 microfarad each. So if you connect all of them in series, obviously the net would be 4 by 3. So this is not the answer. If you connect all in parallel means 3 times 4, 12. Answer is not 6. This is also wrong. So if you connect 2 in parallel and 1 in series, that is yes. Like this. Let us check. If I connect 2 in parallel would be 8 because 4 plus 4 is 8, and this is 4, and these two are in series, so I can write 8 multiplied by 4 divided by 8 plus 4, that is 12, so it will be 8 by 3, and this is also wrong because the answer is not 6. I'll try the last one. Obviously the last one is the answer, but let me show you. 2 in series, 1 in parallel. So 2 in series and 1 in parallel. So 4 in series becomes 2 and 1 in parallel, that is 4, and 2 plus 4 because this system and this system are in parallel, so 2 plus 4 is 6. So obviously D is correct answer, right? Okay, so let's move for next question. Let's see what we have next. Okay, it's a very interesting question. Remember, it says in the figure shown, the charge on the left plate of 10 microfarad capacitor is minus 20 microcoulomb. So we have minus 20, let's say I'm writing in microcoulomb. So this plate has minus 20. So obviously this plate will have plus 20. Okay. And if minus 20 charge is going this way, obviously this will be splitted like this. Okay. And these two are in parallel. Remember, these two are in parallel. V should be same. Potential difference should be same. And potential difference is Q by C. That should be same, means Q should be proportional to C. Q should be proportional to C. So on 6 microfarad I can assume 6Q charge. On 4 microfarad I can assume 4Q charge because the charges on them should be proportional to capacitance. And now you know these two charges, the sum of these two charges is 20. So 6Q plus 4Q, that is 10Q, equals 20. So Q equals 2, means this charge 6Q is actually 12 and 4Q is actually, let's not write it. 4Q is 20. On 4 microfarad we have 4Q, that is 8 microcoulomb. And one more thing. Actually, the left plate is positive, means right plate is positive. Left plate is negative, means right plate is positive. The right plate is positive, it means from here the battery is supplying charge, means from here, or you can say on this side, battery's positive terminal is connected. So on every capacitor the right plate must be positive. Okay, so we have to answer that what is the charge on right plate of the 6 microfarad capacitor. So obviously on the 6 microfarad capacitor, on the right we will have 12 microcoulomb, on the left we will have minus 12 microcoulomb. So correct answer is B, plus 12 microcoulomb. Okay, let's see what we have next. Again, we have a very simple question, and it says the net capacitance, the effective capacitance of this entire combination between A and B is 0.5 microfarad. So if the net capacitance is 0.5 microfarad, what is the value of C? And this question was asked twice in JEE mains. Okay. So obviously there were few difference of numerical values. So I'm not taking that question. I'm sure you will find that question too very easy. So let us solve this one. See, you can say these two are in parallel. So 2 in parallel, this becomes 4 microfarad. And let's see, these two are in series. So 2 and 2 in series becomes 1. This one and this one are in parallel. So 1 and 1, you add 1 and 1, it becomes 2. So this box is of 2 microfarad. And this 2 and 2 are in series. So 2 and 2 in series, it becomes 1. So you can say this branch, the capacitance in this branch is only 1 microfarad. And here in this branch we have a series combination of 4 and 2. So series combination of 4 and 2 gives you 4 into 2 by 6, that is 4 by 3. And now you know this 4 by 3 and 2. Sorry, 1. 4 by 3 and 1. 4 by 3 and 1 are in parallel. So in parallel, I can write 4 by 3 plus 1 and okay. And this whole box is in series with C. So this box into C divided by 4 by 3 plus 1 plus C, it becomes 0.5. Okay, let us solve it. So here you will see 7C divided by 4 by 3 plus 1 is 7 by 3. So 7 plus 3C equals 0.5. Okay. Now if I solve this, let us see what was the value of C. So 14C equals 7 plus 3C, because 0.5 is 1 by 2. 0.5 is 1 by 2. 2 multiplied by 2, 7. It becomes 14C equals 7 plus 3C. And you bring this 3C on the left. 14 minus 3 is 11. So C becomes 7 by 11. And 7 by 11, obviously the option A is perfectly okay. In this question they say, we require a 2 microfarad capacitor in a circuit. And the capacitor should be such that it can tolerate or it can withstand a potential difference of 1000 volt. So we need a 2 microfarad capacitor and we have to apply 1000 volt across this. Okay. And what is available? A large number of 1 microfarad capacitors are available, which can withstand a potential difference of not more than 300 volt. Okay. So we have 1 microfarad and 1 microfarad, we cannot give more than 300 volt on this. Okay. So as potential is divided in series combination, if I add one more 1 microfarad, 300 this can tolerate, 300 this can tolerate. So total voltage we can apply across this combination is 600. Still it is less. Let us apply one more in series. Now 300, 300, 300. 900 voltage, 900 volt we can give. This is also less than what is required. Where requirement is of 1000 volt. Okay. So if I put one more capacitor in series, this will take 300 volt, 300 volt, 300 volt, 300 volt. So we have a system of capacitor which can take up to 1200 volt. If I decrease any one capacitor, the capacity, the voltage capacity will be only 900, which is less. So I will have to take at least 4 capacitors in series such that the 1 kilovolt can be given across it. Okay. But since every capacitor is of 1 microfarad, the net resistance, the net capacitance of this row will be 1 by 4 microfarad. But the requirement is of 2 microfarad. Okay. So this is not actually enough. We will have to add few more rows identical to this, so that every row can withstand or tolerate a voltage of 1200 such that 1000 volt can be given. And see, suppose we have added n rows. So in n rows, the net capacitance should be 2 microfarad. Okay. Actually, the capacitance of each row is 1 by 4 microfarad and all rows are in parallel. We require actually 2 microfarad. So according to parallel combination, the net capacitance of n rows should be equal to n times the capacitance of one row, which is 4, 1 by 4. So this gives you n equals to 8. We need 8 such rows in parallel. And since every row contains 4 capacitors, the total number of minimum required capacitor is 8 multiplied by 4, that is 32. So option A is correct, right? Okay, let's move over to next question. Here they say they have 2 conducting plates, 2 square plates, each of side length A. So this is a square plate. Try to imagine it is a square plate and you are looking at its perfect side view. That is why you are looking at only one dimension of it, right? The plate should be something like this. Right, like this, and the depth is also of A units. So width is A unit and the depth is A unit. That is why we have 2 square plates of edge length A. Okay. Okay. Now there is one more thing. These 2 plates are not exactly parallel. They make a small angle with each other, and that angle is equal to alpha. So here the thickness, the distance between the plate is minimum, and that minimum distance is D, and here the distance is maximum. Okay, so this is a variable thickness capacitor, and if it is a variable thickness capacitor, we are asked what is the net capacitance of this capacitor. So to solve this question, I'll assume this capacitor is made of large number of elements. Like this volume I'll take as one capacitor. Okay, this volume I'll take as one capacitor, and similarly I'll take this as a capacitor, this as a capacitor. Means I have divided my entire system into large number of capacitors placed side by side like this. Okay, if I assume the potential of this plate is V1 and potential of this plate is V2, entire plate will be at potential V2, entire lower plate will be at potential V1. So you can say the potential here is V2 and potential here is V1. So across this elemental capacitance, we have potential difference V1, or you can say V2 minus V1. So if I take any element in this, the potential difference will be V2 minus V1. So you can say all the elements are in parallel, right? All the elements are in parallel. Okay. So let me write the capacitance of this element. Okay. If you're trying to write the capacitance of this element, let's say that capacitance is DC, and according to formula, you know, the capacitance equals to epsilon naught K. So here we have air, so the relative permittivity is 1. So epsilon naught area. The area is a little tricky. Let's see. If this length is assumed to be x, I'll take this width to be dx. Okay, and since the depth is a, this depth inside is a, so area of this plate would be a times dx. Okay, the width is dx and the depth is a, so the area would be a times dx divided by the width. See, this width is d and this width would be, as this is x, this is alpha, this would be x tan alpha, but they are saying alpha is very small, so taking alpha to be very small, the depth, or you can say the thickness, would be d plus x alpha. So this is the capacitance of that element. Okay, if you want to know the capacitance of entire system, all these are in parallel, all these elements are in parallel, and in parallel you simply add C1 plus C2 plus C3. So if you want to add all these elements capacitance together, you will have to integrate this to get the C net And if you want to get the C net, you will have to include every element from here to here. So at this point, the value of x would be 0. And at this point, the value of x would be equal to a. So we have to integrate this from 0 to a. Okay. Now let us make some approximations. Epsilon naught a by d. Let's take epsilon naught a by d common. So inside the integration you will see dx, and as I have taken d common, we will see 1 plus x alpha by d in the denominator, right, from 0 to a. So C net becomes epsilon naught a by d integral, and C, you can write 1 plus x alpha by d, and you take this in numerator, it will become to the power minus 1. So this becomes 1 plus x alpha by d to the power minus 1 into dx. But as this are saying, this alpha is very small, this is very small, this x alpha, if alpha is very small, this thickness, this distance will be very small as compared to d. So in this term you can say this term x alpha is very small as compared to d. And if it is very small as compared to d, I'll open this according to binomial theorem, and I can ignore all the terms except first two terms. So let me open it. Integration from 0 to a, epsilon naught a by d, and here it becomes from 0 to a 1 minus x alpha by d dx, and all other terms in binomial expansion can be ignored because all will have higher power of x. Now if we integrate this, epsilon naught a by d, I'll have 1 dx as a minus x dx is a square alpha by 2d. So take one more a common outside, you will have epsilon naught a square by d, bracket, in the bracket we have 1 minus a alpha upon 2d. So that is your answer, and if you check, I think yes, A is the correct choice. Okay, so I think now this problem is clear to you. Let's move over to next one. So here they are asking us what is the equivalent capacitance of the combination shown. That is a very easy question. As you know, this capacitance is actually shorted. I can just assume the potential of this point as V and potential of this point as 0. I think you all know this. So if the potential of this point is 0, this point potential 2 is 0, and this point's potential 2 is 0. So you can see there is no potential difference across this capacitor. So this capacitor is actually meaningless. In the circuit, this capacitor is meaningless. You can simply remove it, and if you remove it, the two capacitors are in parallel, and if two are in parallel, the net is going to be 2C. Now we will start a very interesting and very important part of this chapter, is inserting a dielectric slab in the capacitor. What we do when we insert a dielectric slab in capacitor, it improves its mechanical strength and also its capacity to store charge and energy. So let us see. Suppose we have a capacitor. Yes, this is first plate and this is the second plate. Suppose I have a dielectric slab, means a insulator's material, and the size and the volume of this insulating material is such that it exactly can fit the volume between plates of the capacitor. Suppose its dielectric constant, or you can say relative permittivity, is ER or K. Okay, so as you know, the capacitance of this parallel plate capacitor, when air is between the plates, is epsilon naught A by D. Okay, but when we fill this gap with this dielectric, what happens? The permittivity of free space is replaced by permittivity of that medium of insulating material, and permittivity, as you know, is equal to epsilon naught epsilon R or epsilon naught K times A divided by D. So can you see the capacitance improves by a factor K, and as you know, K is always more than 1 for all kind of insulating materials. So you can say the capacitance improves by a factor K. So always remember, if a capacitor has capacitance C and you fill the gap between plates with a uniform homogeneous material or medium of dielectric constant K, the new capacitance becomes K times the old capacitance. Okay. So let us now learn what and how it affects the capacitor in circuits. Okay. So I have divided this study into two parts, and the first part is when we have an isolated charged capacitor. What do you mean by isolated? Isolated means it is not connected to any circuit or any battery, or you can say initially this would have been connected by a battery, it is charged and now the battery is disconnected. So suppose we have an isolated capacitor, there is air between them, and the charge and the plates of the capacitors have charges Q and minus Q. Now if I fill this gap with an insulating medium of dielectric constant K, okay, so the new capacitance, suppose I am representing the capacitance after putting the dielectric slab as C prime, so the C prime would be equal to K times C, where C stands for capacitance before inserting the dielectric. Okay. What is the new charge on the capacitor? See, the charge on the plate was Q, and the charge has no way to escape. The charge cannot go anywhere from the plate because the plate is isolated. It is not connected to any other part of the circuit or any other conductor. So charge cannot escape, and if charge cannot escape, obviously the charge after inserting the dielectric slab is going to be the same as it was before. So Q dash is equal to Q. No change. No change in charge. Always remember, in isolated capacitor, there is no change of charge. Okay. Okay. So what happens to the potential difference between the plates? As you know, potential difference is equal to Q by C. So Q is now same as before, and the new capacitance is K times C. So I can write Q by C as the old potential difference divided by K. So you can see, as K is always more than 1, inserting a dielectric slab in a capacitor, in an isolated capacitor, decreases the voltage by a factor of K. Okay. So this is the new voltage. Okay. Also the electric field inside the capacitor decreases by the same factor, E old divided by K. Remember? Okay. The new potential energy in the capacitor. What is the new potential energy in the capacitor? As you know, the charge is same, so I can write the potential energy as Q square divided by 2 C dash, because I am writing the new potential energy. So charge is still the same, there is no change in charge. So the same charge Q square divided by 2 into new C, and new C is K times C. So you can say Q square by 2C as old energy, so it is U divided by K. Okay, so energy gets changed. Okay, and you can also see the energy is decreasing. Okay, let us understand this a little detailed. Okay, what happens when I put a dielectric slab in a capacitor? Suppose this is the positive charge of plate, this is the negative charge. Actually the charge appears on the inner face of the capacitor plates, but I have drawn it outside as there is no space inside. Because of this charge, there is some induction, and near the positive charge, negative charge induces, and near the negative charge, positive charge induces. When these induced charges interact with plates charges, they feel an attraction force like this. So this plate is actually pulled by a force, okay, by a force, and this force may be called as internal force or force by electric force or force by the capacitor on the slab. And as capacitor is moving in, the displacement is also in the direction of force. So we can say the electric forces or the capacitor does positive work on the what? On the dielectric slab. Okay. And as you know, if a internal force of a system is doing positive work, if internal force of a system does positive work, what happens? Obviously the energy decreases, the energy of the system decreases, and that is why we have seen the energy, the new energy is k times smaller than the old energy. Okay, so by the basic concept of work done and force, you can say work done by internal force is equal to negative of change in energy. So work done by internal force becomes, as you know, change is represented by U2 minus U1. So minus of change will be equal to U initial minus U final. That is U minus U by K. If I write U as Q square divided by 2C, take this common and we will have 1 minus 1 by K. This is actually the work done by internal force or force by the capacitor on the slab. Okay, but this force will accelerate the slab if we can ignore the friction and air resistance, and this slab is going to have a lot of kinetic energy because of this work when this slab goes completely inside. Okay, if we let this slab go like this, it will gain some kinetic energy, it will overshoot outside, then it will be pulled again back inside the capacitor, it will again gain some kinetic energy, it will overshoot on the left side, and ignoring air resistance and the friction between plates and capacitor slab, experimentally we found that the slab oscillates like this. Okay. So what we do actually, we apply some external force also, and we let this slab go inside the capacitor very slowly, and in that case there is no change in kinetic energy. So according to work energy theorem, you can write work done by external force plus work done by internal force is equal to, as it is equal to change in kinetic energy, and that is 0. So this is equal to 0. And if it is 0, work done by external force, if you are asked, you can write it as equal to minus of work done by internal force, and this is the work done by internal force. Always remember. So these are few very important points. There is one more point, let me tell you. When the slab completely enters the volume between plates like this, please ignore this air gap. This air gap is actually very small, means the air gap between plates and dielectric is actually very small. And here you can see, if this is the positive plate, on the positive plate we have positive charge, let's say Q. On the negative plate we have negative charge, let's say minus Q. So these charges have some induction effect on the dielectric slab, and on the surface of dielectric slab some charge get induced. Okay, so near positive plate we see some negative charges induced, and near negative plate we see some positive charges get induced. This you can write as Q induced negative and this as plus Q induced. Always remember, near positive plate we have minus Q negative charge induced, and near negative plate we have positive charge induced. Okay, so always remember, I'm not deriving it, so just remember Q induced, the magnitude of induced charge is given by the total charge Q on any one plate multiplied by 1 minus 1 upon dielectric constant of the slab. So these are the few fundamentals you should remember. The first is capacitance. Capacitance changes by a factor of K. The charge in case of isolated charge capacitor do not change. The voltage is reduced by a factor K. The electric field is reduced by a factor K. The potential energy is reduced by a factor K. Work done by internal force is given by this. Work done by external force is given by this, and induced charge on the surface of dielectric slab is this. So these are the few fundamentals related to this and which will help you a lot in solving many problems. And obviously, as you can see, we have explained, we have learned many concepts, so there can be many questions made based on this story. Okay. The next cases. In the first case, I took an isolated charge capacitor. Now I am taking a capacitor which is connected to a battery. So as you know, initially I am taking a capacitor and air is between them, right? If air is between them, now if this switch is closed, within no time, within almost you can say few nanoseconds, the capacitor is completely charged, okay, and the charge on capacitor becomes plus CV and minus CV. I think you know this already. Okay, so let us learn the first very important thing. The new, if we again fill this capacitor with the dielectric of constant K, the new capacitance becomes K times C. That is simple. Okay, if air is replaced by some medium, the permittivity will be replaced by that medium, and we will have capacitance, new capacitance as K times C. Okay, this time let us think about voltage. Okay, actually just look carefully. This capacitor is connected to this battery. So if potential of this point is 0, let's say this potential is 0, obviously this point's potential is going to be V, this point's potential is going to be 0, and this point's potential is going to be V. So whatever change you make here, the potential difference across capacitor is going to remain V because it is connected to a battery, because battery maintains a constant potential difference across it. Okay, so this time when the capacitor is connected to a battery, the potential difference across capacitor will remain same. Okay, so V dash is equal to V. There is no change in potential. Okay, if potential is not going to change, obviously the electric field is not going to change. The new electric field is same as the old electric field E, right? Yes, the new charge, as you know, the charge is equal to C times V. V is same, but C is increased, so new charge is going to be K CV, means the charge is going to increase by a factor of K. Okay, the new charge is K CV. So if, just think of it, if initially on plates we have plus CV charge and finally we have plus KCV charge, it means some charge has flown through the battery on the capacitor plates, and the charge flown in these wires is going to be delta Q, and delta Q is going to be the new charge minus old charge, and that would be K minus 1 CV. This is the charge flown through battery. Okay, and if charge is flowing through battery, battery does work. Remember, battery does work. So let me write work done by battery. Work done by battery, and as you know, work done by battery is simply the charge flown through the battery multiplied by EMF of the battery. So delta Q times V gives you K minus 1 CV square. Okay. Okay, yes. Next point. Obviously, the initial energy on the capacitor was half CV square. But as capacitor increases by a factor of K, the new energy becomes half K times CV square. Remember, the old energy was half CV square only. So energy increases by delta U as new energy minus old energy, and that will be half K minus 1 CV square. Okay. Actually, in this case also, because of the induction effects, the capacitor pulls the dielectric slab inside when this slab was being inserted. Because of that, capacitor again does some positive work, and if we let this slab go inside capacitor very slowly, we will have to exert a force outward to make it go slow, and we can say some external agent is also working. So if insertion of slab is slow, if insertion of slab is slow, what you can say is work done by all external agents is equal to delta U. Work done by all external agents is equal to delta U. Okay, or simply let me write it in more simpler form. Work done by external force plus work done by internal electrical force plus work done by battery equals 0, because total work equals to change in kinetic energy, and we are letting the slab go only slowly. So there is no change of kinetic energy. And as we know, the work done by internal force is equal to negative of change in potential energy, negative of change in energy. So I can write work done by external force plus work done by battery, and this I can write it as minus delta U equals to 0. So it gives you work done by external force plus work done by battery equals to delta U. Let me put values of everything. So work done by external force plus work done by battery, which is K minus 1 CV square, equals to delta U as half K minus 1 CV square. So work done by external force now becomes minus half K minus 1 CV square. This is the work done by external force. I don't recommend you to remember every formula here. Just try to remember how to find delta U, work done by battery, and using this equation, work done by external force plus work done by battery equals to delta U, you can find work done by external force. Okay, so this is the way we calculate work done by external force. Again, the induced charges, the formula for induced charges is same. It will be Q on plates multiplied by 1 minus 1 by K. So here in this case, as initially the charge was less on the plates and later the charge on the plate is increased, that is why the induced charge will also increase, and induced charge on the dielectric Q induced the magnitude of Q induced on any one phase of dielectric can be written as new charge KCV times 1 minus 1 upon K, the same formula. Okay. So these are few fundamentals that you have to remember. Okay. So learn them one by one, practice them first and then go for solving questions. Okay. So I'll again say you pause this video, learn them well and then go further with this session. Okay. So let us solve few problems, few simple problems based on this. So in this question we have a capacitor and there is a parallel plate capacitor, and when air was in it the capacitance was 6 microfarad. So I can say the C is 6 microfarad, capacitance is 6 microfarad when there was air in between the plates. Okay, but when we fill some dielectric medium, the new capacitance becomes 30 microfarad. Actually, this is not a millifarad, it is microfarad. There is some typo error. So it is again mu equals to, sorry, the new capacitance becomes 30 microfarad. So I can write C dash as 30 microfarad. But as you know, the C dash is equal to K times old C. Just put C as 6 here, you will find K equals to 5. And you know they are asking you the permittivity of the medium. So as you know, the permittivity of the medium is given by epsilon naught epsilon r. Epsilon r is nothing but dielectric constant. So you can multiply this epsilon naught by dielectric constant, and if you multiply 5 with epsilon naught this, the value will be very close to D. Okay, so that is your answer. Over to next question. Okay, so again this is a very interesting question. It says capacitor of capacitors 9 microfarad having dielectric slab of constant 2.4 strength. 2.4 is the dielectric slab's dielectric constant and dielectric strength is 20 millivolt per meter. What is dielectric strength? Actually, dielectric strength is not dielectric constant. Dielectric constant is K, which is given by here as 2.4. Let's put a comma here. Dielectric strength is actually the maximum electric field that can be applied across a capacitor or across any medium. So this is the electric field, and I think you are seeing the unit also. So according to unit also, this is megavolt per meter. So volt per meter is the unit of electric field. So always remember, dielectric strength is actually the maximum electric field we can apply across a medium. So it says the dielectric slab of dielectric strength 20 megavolt per meter. It means across that dielectric slab, the maximum electric field we can apply is this. They are asking us the area of the plates. Okay, so just imagine we have made a capacitor, we have put some dielectric, and the maximum potential difference across it is 20 volt. The maximum potential difference across it is 20 volt. So if I consider the gap between plates as D, obviously the electric field between them is going to be V by D. But as we are using maximum voltage, we will get maximum electric field, and maximum electric field is equal to dielectric strength, remember. So this is equal to 20 times 10 to the power 6 volt per meter, because it is megavolt per meter. So let's find D. If you put V max as 20, you will find D as 10 to the power minus 6 meters. Okay, this is the distance between the two plates of the capacitor. Okay, now they are asking us what is the area of the plates. You know D, and you know the capacitance is equal to epsilon naught K times area and divided by D. And let us see what we know. We know the capacitance 9 nanofarad. We know the value of epsilon naught We always remember the value of epsilon naught as 8.85 multiplied by 10 to the power minus 12 in SI units. We know K is 2.4. Area we have to know, and D we have calculated. So the area will be equal to C, that is 9 times 10 to the power minus 9, because C is 9 nanofarad, multiplied by D is 10 to the power minus 6, divided by epsilon naught is 8.85 times 10 to the power minus 12, and K is 2.4. Okay. Okay. See, 8.85 is very close to 9. So if I just think this and this got cancelled, the answer should be very close to 1 upon 2.4. 1 upon 2.4. The numerical value will be should be actually very close to 1 upon 2.4, and 1 upon 2.4 is nearly 0.4. So option B is correct because it is 4.2. Okay, so you can check the calculations and you will find the order also very close to this. So this is the answer. Okay, in this question they are saying a parallel plate capacitor having capacitance of 12 picofarad is charged by a battery of 10 volt, battery of EMF 10 volt. Okay, and the charging, after charging, battery is disconnected. So if battery is disconnected, okay, so now we have an isolated charge capacitor, and charge on it is say plus minus Q, and obviously the Q would be equal to C times V, right? Now they are asking if now we put a porcelain slab. Porcelain is a kind of insulator, so porcelain slab is simply nothing but dielectric slab of dielectric constant 6.5 is now slipped between the plates. What will be work done by the capacitor on the slab? See, the work done by the capacitor is actually the internal force, is the internal electric force, and you know the work done by internal electric force or work done by the capacitor is equal to negative of change in potential energy, that is final energy, minus initial energy. Okay, so this will become initial energy minus final energy. Let us see what is initial energy. If I take capacitance as C, Q as CV, the initial energy is going to be Q square, that is C square V square, divided by 2C, that is CV square by 2. Okay, and the final energy would be C square V square. Why I am doing C square V square? Because the charge is same. As the battery is disconnected, the charge will remain same. So initially the charge was CV, the now charge will remain CV. So Q square is C square V square, and divided by 2 times the new capacitance Kc. Okay, so let's put the values here, and you will get UI, UF, you will get half CV square common 1 minus 1 by K. Okay, so let's put all the values, and C as 12 picofarad, the V square as 100 because V is 10, and the K as 6.5. You will get an answer very close to 5.08 times 10 to the power minus 10 joule. So if you check options, it will be close to option A. Okay, so over to next question. Now this time we have again voltage rating of a parallel plate capacitor is 500 volt. Voltage rating means we cannot place a voltage more than 500 volt across it. This is the meaning of voltage rating. Dielectric can withstand a maximum electric field of 10 to the power 6 volt per meter. So you can say that the dielectric strength of the dielectric medium is 10 to the power 6 volt per meter. The plate area is given, the dielectric constant of the capacitance is dielectric. What is the dielectric constant? They are asking you what is the dielectric constant if capacitance is 15 picofarad. Okay, so as you know, capacitance is given by epsilon naught K A by D. Here you are given C, epsilon naught, K they are asking, area is given, let's find D. And as you know, the E, the electric field inside capacitor is V by D. So obviously the E max will be equal to V max divided by D. V max they are saying as 500 and maximum electric field is actually the dielectric strength, which is 10 to the power 6. So we have D as 500 divided by 10 to the power 6, that is 5 times 10 to the power minus 4 meter. Okay. So let's put all the values here and we will have K as C, which is 15 picofarad, 15 times 10 to the power minus 12. Okay. D as 5 times 10 to the power minus 4 divided by epsilon naught area. Epsilon naught is 8.86 times 10 to the power minus 12. So these two got cancelled. And area is 10 to the power minus 4 and minus 4. So these two got also cancelled. So we have nearly 15 times 5, that is 75 divided by nearly 9. So if you make some calculations, 75 by 9 is roughly 8 point something. So the correct option should be B. Okay, that can be easily guessed. Okay, so over to next question. This time they are saying a combination of parallel plate capacitor is maintained at certain potential difference. Okay, now when a 3 mm thick slab is introduced, so suppose we have capacitors, one capacitor is this, and we have introduced a 3 mm slab, 3 mm slab. Okay, in order to maintain same potential difference, the distance between plates is increased by 2.4 mm. Okay, find the dielectric constant of the slab. See, actually, initially you can say the capacitance was epsilon naught A by D. But when you have inserted the slab, to get the same things again, obviously you should have same capacitance again. If the capacitance is same, there will be same potential difference. So I should say the new capacitance with increased width and when with dielectric constant, the new capacitance should be same as the old one. So the new capacitance can be written as epsilon naught A divided by, as I have inserted dielectric slab and then we have increased the width. So obviously the dielectric slab is not filling the entire space, and in that case the formula is the new width minus thickness of dielectric and plus thickness of dielectric divided by K. If you do some calculations, you will see the D will be equal to D dash, the new thickness is old D plus 2.4 minus thickness of dielectric is 3, I'm taking all in mm, and plus 3 divided by K. So solve this and you will find D will be cancelled and K will be equal to 5. So correct answer is obviously C. Okay, so next question. In this question they are saying a parallel combination of two air filled capacitor of capacitances C and NC is connected to a battery of voltage V. So what we have here is two capacitors C and NC, they are in parallel and they are connected to a battery of voltage V. So obviously both will be charged by a potential difference V. Okay, so initially you can say, and now battery is removed actually. So initially they have this C and NC. As it is charged to potential difference V, the charge here should be CV, and it is also charged to same potential difference V, so charge here should be NCV. Okay, plus minus plus minus. And now they are inserting a dielectric slab of constant K, and they are asking us what is the new potential difference of the combination. Okay, so finally we have this, and in capacitance of capacitance C we have inserted dielectric, so its capacitance is going to be Kc, and let us assume the final potential is V final, and as they are in parallel, potential on both would be V final, and we will now conserve the charge of these two plates, as the charge of these two plates will remain between these two plates, as these two plates are isolated, electrically isolated from the right part. Okay, so let's write conservation of charge. Initially we have CV plus NCV, and now we will be having KCV final plus KNCV final. Obviously you find V final, cancel C from everywhere, and you will have V final as 1 plus N times V divided by K plus N. Okay, so your correct answer is D. Okay, next question. Yes, this time we have a capacitor again. Capacitor is 5 microfarad. If the plates are pulled apart to reduce the capacitance to 2 microfarad, how much work is done? If they ask you how much work is done, and when nothing is specified who is doing this work, always remember you have to find by default work done by external force. Okay, so as the capacitor is charged to 5 microcoulomb, okay, and it is not being said that it is connected to battery, so we will take it an isolated capacitor without connected to a battery, so charge on the capacitor will remain same. So we have a capacitor 5 microcoulomb, 5 microfarad, and the potential, the charge on it is 5 microcoulomb. Let's say charge is Q and capacitance is C. Okay, or C1, let me say C1. Okay, and as it is not connected to battery, you can always say work done by external force is equal to change in potential energy, or you can say U final minus U initial. As battery is not doing any work, so the only external work is work done by external force. There is no work done by battery. So this is equal to delta U, right? As the charge is going to remain same, I can say the final energy would be Q square divided by 2C2 minus initial energy would be Q square divided by 2C1. Let's write Q square as 25 times 10 to the power minus 12 divided by 2. Let's take it common, and we will have 1 by C2 as 2 10 to the power 6 minus 10 to the power 6 divided by 5. Okay, in SI systems, I have changed everything in SI systems. Okay, as capacitance is 2 microfarad, so micro I have removed by multiplying it by 10 to the power 6. Okay, so let us solve this, and after solving this, you will have 25 by 2 multiplied by, I think, 3 by 10 and multiplied by 10 to the power minus 6. So solve it and you will have 3.75, because 75 by 20 is 3.75 times 10 to the power minus 6 joule. So B is the correct answer. Okay. Next question. This is again a very important question. So let us study. This time we have a parallel plate capacitor again of area. The whole area is 6 centimeter square. Let me consider this area as A. The whole area is A. Okay. Actually, the area is divided into 3 parts. So I can say this area is A by 3. This area is A by 3. And this area is A by 3. Okay. And these 3 1/3 areas are filled by three slabs of dielectric constants K1, K2 and K3, where K1, K2 and K3 are 10, 12 and 14. Okay. And they fill the entire gap of 3 mm. Let's say gap is 3 mm or T. So actually, this is the entire plate, and this plate is at same potential, because you know all points of a conductor are at same potential always. Okay. So the potential difference between these 2 points, potential difference between these 2 points and potential difference between these 2 points are same. So if we think of this capacitor as made of 3 capacitors like this, all 3 are connected in parallel, as potential difference is same across all 3. So let me write the net capacitance as C net, and it will be equal to C1 plus C2 plus C3. Just concentrate on the first capacitance. As you know, the capacitance can be written as epsilon naught K. K is K1, area is A by 3 and divided by D. Right, this is the first capacitance, plus epsilon naught K2 A by 3 divided by D, second capacitance, plus epsilon naught K3 A by 3 divided by D. This is the third capacitance. This is the net capacitance of this combination. Now they are saying the dielectric constant of a material which when fully inserted in above capacitor gives same capacitance. So now please assume that a uniform dielectric is placed in the space between plates, and then the capacitance would be epsilon naught Ka by D, because it fills the entire area. And now if this capacitance is same as the old one, this two should be equal. Okay, and if these are equal, let's cancel epsilon naught by D, epsilon naught by D, epsilon naught by D, cancel from everywhere, A cancelled from everywhere, and you will see K as K1 by 3 plus K2 by 3 plus K3 by 3, K as K1 plus K2 plus K3 by 3. So 10 plus 12 plus 14 divided by 3 gives you 36 by 3. So K would be equal to 12. And that is your answer. Next question. This is a good one. This question says a parallel plate capacitor has plates of area A separated by distance D between them. Okay. So the plate area is A and the distance between them is D. Right. It is filled with a dielectric which has a dielectric constant that varies as K as a function of x equals to K times 1 plus alpha x, where x is the distance measured from one of the plates. So it says if you are looking from one plate at a distance x from it, at this point K will be given by this function. And as you move further, the K is going to increase as it is a linear function of x. So K is increasing in this direction. So if what we will have to do, we will have to divide this entire volume of capacitor into large number of elements, this kind of elements, like we place books in shelves. Okay, and every book ahead of the first book will be having a greater dielectric constant as dielectric constant increases as x increases. And one such element is this at a distance x from one plate, and its dielectric constant is given by this. And since all these elements are placed side by side, they all can be considered in series. So let me write the capacitance of any one element. The capacitance of this element can be written as C equals to epsilon naught A, k is k times 1 plus alpha x divided by thickness. And can you see the thickness of this element is a small increment of x, that is dx. So dx. And remember the point, all the elements are in parallel. And if all the elements are in parallel, what you know is the C net is given by 1 upon C net equals summation of reciprocal of all element capacitances. Okay. So let me put the value of 1 upon C here, and summation, by summation we can replace summation by an integration sign, and 1 upon C would be C. 1 upon C would be dx divided by epsilon naught Ka 1 plus alpha x. And see, x is varying from 0 to d, because the first element will be at x equals to 0 and the last element would be at x equals to d. Okay. So we'll have to integrate from 0 to d. Let's do some transformation. They have given you something. They have said that alpha d is very, very less than 1. Okay, alpha d is very, very less than 1. So if alpha d is very, very less than 1, all x are less than d. So all alpha x is also extremely less than 1. And if alpha x is less than 1, I can rewrite it like this: 1 upon epsilon naught Ka, and inside integration I can write 1 plus alpha x to the power minus 1 dx. And I can expand this binomially, and as alpha x is very small, its higher order terms can be ignored. And if higher order terms can be ignored, I can write this as, from 0 to d, as 1 upon epsilon naught Ka integration of 1 minus alpha x dx from 0 to d. Let's integrate. We will have 1 upon epsilon naught Ka d minus alpha d square by 2. Okay. And now flip it and you will get C net as epsilon naught Ka divided by, take d common, and you will left with 1 minus alpha d by 2. Again, I can make this transformation as no option is like this. No option is like this. I can make another transformation. I can bring this denominator in the numerator, and I'll put it as epsilon naught A K divided by d and 1 minus alpha d by 2 to the power minus 1. Again, expand this exponentially. Alpha d is very small, so alpha d by 2 is also very smaller than 1. So I'll keep only 2 terms of binomial expansion, and I can ignore all higher order terms of alpha d. So in the answer we would have epsilon naught A K by d and 1 plus alpha d by 2. And this matches with this AK epsilon naught by d 1 plus alpha by d by 2. So A is the right answer. Okay. Now we have the last part of this chapter, and it is transient state of RC circuit. We have seen RC circuits, but whenever we have seen RC circuits till now, we have seen them in a steady state. Okay. Let me brief it a little. Whenever you connect a capacitor with a voltage source without a resistance, imagine there is no resistance here. Whenever you have connected a capacitor with a voltage source, Initially large currents, almost infinite current flows, and instantly the capacitor is charged and current stops. This is what happens in a capacitor circuit when capacitor is connected to a battery. Initially infinite currents flow and capacitor is charged in no time. But when we use a resistance, the resistance limits the current. If resistance limits the currents cannot take a very large value. So charging of capacitor will take some time. The charging of capacitor will take some time and the final charge will take time to reach. So for some time the circuit remains in transient state. The current exists in this circuit for some finite time. The charge on capacitor changes for a finite time and then it becomes constant and comes in a steady state. So till the moment we have current in the circuit, till the moment the charge is changing in the circuit, we call this period as transient state. And when current in the circuit becomes zero, the charge on the capacitor becomes constant. After that we say the circuit is in a steady state. Okay, so that is the meaning of transient state. So here we have few assumptions. There are two parts of this study. First we will discuss the charging of capacitor and then we will discuss its discharging. So in charging of capacitor, this is the simplest loop. We have a capacitor, initially uncharged capacitor. I am assuming there is no charge. So I am assuming zero initial charge on the capacitor initially, right? A battery connected to it. And we have also a resistance. Okay, so because of resistance, the process of charging delays. And the process of charging, the period of charging is said to be transient state of RC circuit. So let us close the switch. So we assume at t equals to 0, we close the switch. Okay, and as the moment we close the switch, the current starts in the circuit. If current goes like this, let's say current is I, this current charges the capacitor. So suppose at some time t, the current is I, the charge on the capacitor is Q, it's not its final value, it is increasing because current is charging the capacitor. So at the moment t, I have assumed the capacitor has gained Q charge, but it is not the final charge. Current is still there, it is increasing the charge, right? You can also write the rate of increase of charge as I, dq by dt as I. Okay. And now let's write KVL in this equation like this. If you start from this point, I'll write V, I've crossed battery. Then let us cross the resistance. When we cross resistance, I'll write minus IR. And when I cross the capacitor, I'll write minus Q by C equals to 0 because we reached this point. This is the basic KVL of this circuit after time t from the beginning. Okay. I can replace by dq by dt. So I'll write V minus Q by C on the left and IR on the right, and IR can be written as dq by dt times R. Okay. And then I'll take C common. Let's bring dt here. So dt divided by, let's bring R also on the left, R, C, and let's bring dq divided by CV minus Q. This is the differential equation between the variable charge on capacitor and time t. You can integrate this differential equation, and here we will apply limit from 0 to t. So at t equals to 0, we had no charge on capacitor, and at t we have Q charge on capacitor. So let's integrate this, and after integration, I think that part is simple for you. So after integration, you will get the Q as CV times 1 minus e to the power minus t by RC. Q equals CV times 1 minus e to the power minus T by RC. This is the charge on the capacitor of a charging capacitor as a function of time. If we have only one loop circuit with one battery, one resistance, one capacitor, and capacitor is initially uncharged, it is applicable in that case only. But remember, this case is very important as far as examinations are concerned. Obviously, we have very few questions asked based on this. So, as far as NEET and JEE mains is concerned, it is not that much important. Okay, only once or twice they have asked few questions, and whatever question they ask, they are in these two exams, these questions are based upon the very simple loop that we learn here. They don't give you any complicated loop. Okay, they give you a single loop problem with a capacitor, a resistor and a battery and an initially uncharged capacitor. Always remember. So here this formula is applicable. If the formula is complicated, we can again write KVL in that. Okay, we don't have to remember any formula, right? We will write KVL in that circuit and we will have to solve it for every new situation. Okay, so that is the Q. As you know, the power of exponent are always dimensionless. So as the unit of t is time, the second, the unit of RC must also be second, such that the exponent can become dimensionless, right? So always remember, t upon RC is dimensionless. So RC, the dimension of RC must be times dimension. So as RC has a dimension of time, the RC is called time constant of this RC circuit, and it is represented by a letter tau. It is represented by a letter tau. Okay. Let us see what happens after one time constant. Let us see what happens after one time constant. If I put time as one time constant, mean RC in this equation, I'll have CV times 1 minus e to the power minus RC by RC, that is e to the power minus 1, which is 1 upon E. Always remember, 1 upon E is 0.37. And if 1 upon E is 0.37, 1 minus 1 upon E is 0.63 times CV. So what we learn from here? We learn after one time constant, the charge on the capacitor becomes only 63% of maximum charge CV. 63% of maximum charge CV. Okay. So this is the result you should remember, I think, because they ask you sometimes directly what is the charge after one time constant. So in charging circuit, after one time constant, the charge will be 63% of maximum charge CV. Okay. If I put t equals to t tending to infinity, means if I want to take charge after a very long time, we should replace t by almost infinity, and e to the power minus infinity is actually 0. So at this time t tending to infinity, we will have e to the power minus infinity as 0, so charge will be CV. So you can say after a very long time from the beginning, the charge becomes CV. So this is the ultimate charge. If I would have not used the resistance, the charge would be CV on the capacitor. If we use resistance, still the charge is CV. But in this case, with resistance, charging takes time. So resistance never changes the final charge on capacitor. Resistance only just delays the process of charging and makes the transient time a little longer. Okay. So, okay, this is charge. The charge as a function of time means this function is represented by this graph here. Okay. So we have charge and time, and the ultimate value of charge is CV, and you can see the charge slowly grows and finally after a very long time it becomes almost equal to CV. Theoretically, the charge will be equal to CV after infinite time, but practically we see after maybe 4 or 5 time constant, nearly 4 to 5 time constant, the charge becomes very close to CV. And after 1 time constant, yes, this is the very important data. After 1 time constant, the charge is 0.63 times of CV. This you should remember. Okay. This is the charging part. If in some question they ask you what is the function of current, what is current as a function of time in that circuit, current can be found from the equation I equals dq by dt. So simply what you do, simply differentiate this equation, and if you differentiate this equation, you will get current as a function of time as V divided by R e to the power minus T by R. So this is the value of current as a function of time in the circuit. Okay. As you can see, this function is a decreasing one. So current in the circuit decreases as time increases. Its initial value is V by R. This is time. And after 1 time constant, remember after 1 time constant, here we will get e to the power minus 1. That is 1 upon e. And I told you 1 upon e is 0.37. So after 1 time constant, the current in the circuit will be 0.37 times of maximum current, which is V by R. Okay. So that is about charge and current. If in some question they ask you what is the potential difference across resistance, just multiply I by R. You will get potential difference across resistance. If they ask you what is the potential difference across capacitor at any point of time, the potential difference across capacitor would be Q by C. You know the value of Q as a function of time. So this is the simple idea of charging of a capacitor. Then we will discuss discharging of capacitor. Obviously, discharging will take place after charging. So initially I have assumed at t equals to 0, the charge on capacitor is Q naught. So on one plate we have plus Q naught, on other plate we have minus Q naught. But this charge is at t equals to 0 initially. But as I close this switch at t equals to 0, the charge begins to leak through this path, and the flow of charge is termed as current. So charge begins to leak. So if at time t, I assume the current in circuit is I and the charge on the capacitor plate remains is only Q minus Q. This is the charge after time t, this is the current after time t. Okay, now as the current is decreasing the charge, can you see the current is away from positive charge? This current is draining the charge away. So by this current, charge will decrease. And current will be actually equal to the rate of decrease of charge, that is minus dq by dt. So here always remember the current is equal to minus dq by dt. Now if you apply KVL from here to here, you will get Q by C, and from here to here you will get minus IR equals 0. Bring this IR on the right side, on the left we will have Q divided by RC equals to minus dq by dt, because I is replaced by minus dq by dt, and let's bring Q on one side, time on one side. So dt divided by RC becomes minus dq by Q. Integrate the result, and now you know at t equals to 0 we have charge as Q naught, and after some time t the charge is only Q. So integrating this, you will get, yes, you will get the charge as a function of time as initial charge Q naught and e to the power minus t by R. So here in this question, here in this case, the charge decays. The charge decays. The initial charge is Q naught. This is charge as a function of time. And after one time constant, the charge is, as it is decreasing, let's put the value of time constant. If we put time as RC, that is one time constant, we will have e to the power minus 1. And the value of 1 upon e, or e to the power minus 1, is 0.37. So after one time constant, the charge would be 0.37 times initial charge. If you want to find current in the circuit, just do I as minus dq by dt. And minus dq by dt would be I equals Q naught by RC e to the power minus t by RC. That is the value of current in the circuit. And as the graphs, as the functions of Q and I both are similar, they both have some constant followed by e to the power minus t by RC, the graph of I here would too be like this. Okay, so that is about discharging of capacitor. Now it's time for few questions. Okay, in this question they are saying the figure is showing an experimental plot of a capacitor in RC circuit, a discharging capacitor in RC circuit. Okay, and if it shows the plot of a discharging circuit, okay, the time constant of this circuit lies between. They are asking us time constant of the circuit lies between. As you know, the functions of discharging circuit are like this: Q equals initial charge and e to the power minus t by RC. Okay, so if I replace t by time constant, time constant is RC, we will get e to the power minus 1. So Q after one time constant would be Q naught by E, and as I told you, 1 upon E equals almost 0.37. So 0.37 times Q naught. Okay. Initially, as you can see, the initial value is 25. Q is symbolic, it can be voltage also, can be current also, it is just the initial value. So Q naught, the initial value is 25. So we have nearly 0.37 multiplied by 25. 25 we can write as 100 by 4. So we have nearly 37 by 4. And 37 by 4 is nearly 9.25. So see, 9.25 is actually between 10 and 5. Somewhere here we will be having 9.5. And if I make this line and this line, see, the time is between 150 and 200. So time constant lies between 150 and 200, and the option A is always obviously correct. Over to next question. Here they are saying we have two capacitors in series and they are connected to a battery and a resistance, and when switch is closed, the charge on capacitor C1 as a function of time will be given by. So this is actually a very simple problem. You can replace the two capacitors by a single capacitor of capacitance C net. You can forget about this capacitor. You can take C net as a single capacitor, and obviously the C net will be given by C equivalent. C net can also be called as C equivalent and will be given by C1 C2 divided by C1 plus C2. Okay. Yes. As the two capacitors were in series, those two capacitors will have same charge always, and if they are replaced by this single capacitor, that single capacitor will too have the same charge, as it has to be equivalent of those two. So if you find the charge on this C net, the same charge will be on C1, the same charge will be on C2 as they are in series. So let me find the charge on C net as a function of time, and that would be answer of the charge on C1 as a function of time. As the charge as a function of time is given by C EMF of the battery E, and as it is a charging circuit, we will have 1 minus e to the power minus t by RC. What do you have to do? You have to just replace C by C net or C equivalent. And let us see where we have C as C equivalent. Yes, in this A, option A. So option A is correct. So that was all about charging, discharging, dielectrics in capacitors and circuits. Okay. So that was everything in chapter, and I explained it up to NEET and JEE mains level. Okay. In the next course, we will be dealing with all concepts and all questions which are very helpful for JEE advanced also. Okay. So this is all for this chapter now. Thank you so much, and I wish you again all the best for your exams. Thank you so much.